Good morning, good afternoon, good evening, wherever you are. And my name is John Kweku Otu. I'm a professional electrical engineer, and will be getting my PhD at the end of December 2022 from University of Idaho. My presentation title is Protection Scheme of an Offshore Wind Farm that is integrated to an MMC-based HVDC transmission system. And MMC means modular multi-level converter. Now let's go to the next slide. The next slide basically talks about the outline. And first, I'll talk about the introduction, and with the introduction, I'll give a little bit background about this topic. Then I'll talk about the current fault detection techniques that is in HVDC, high voltage DC transmission system. Then I'll talk about the advantages and drawbacks of the current fault detection techniques that we have in high voltage DC transmission system. Then I'll talk about the current fault processing techniques that we have in HVDC. Then pivot on the advantages and disadvantages of the current fault processing schemes that we have in HVDC. Then I'll talk about the challenges with DC fault detection and interruption as applicable to high voltage DC transmission system. All this will be part of the introduction that I'll speak about. Next, I'll describe the problem statement and basically the objective to mitigate the problem statements by coming up with solutions. Next, I'll talk about the influencing factors in protection, detection, localization, and classification of HVDC fault protection scheme. Next, we'll talk about what is an HVDC, what is high voltage DC transmission system, and the application of high voltage DC transmission system. Next, I'll give a little bit background about the timeline evolution of high voltage DC transmission system. Advantages and disadvantages of HVDC when compared to HVAC. That is when you make a decision or a choice to decide on implementing an HVDC technology compared to a high voltage AC technology. Next, we'll talk about the different configurations that we have in high voltage DC transmission system. Then we'll talk about the high voltage DC technologies types that we have over there. As you know, we have two types of high voltage DC technologies, that is LCC and the voltage source converter. Then we'll talk about the modular multi-level converter voltage source converter technology that we have, and that is basically the focus of this presentation. Next, we'll talk about the components of a voltage source converter. Then the general equation for power transfer in a voltage source converter HVDC transmission system. Then we'll talk about the control schemes that we have for the voltage source converters. Then the different types of wind turbines that we have. Next, the test topology or the schematics that I have modeled in PSCAD software platform. We're going to talk about hybrid DC breaker technology, and that is the breaker that needs to be utilized in a selective fault protection scheme. As HVDC voltage source converter technologies evolved from a point-to-point to a multi-terminal DC configuration to a DC grid. Next, I'll give a brief description of half-bridge submodule MMC and its DC fault characteristics. Next, I'll give a presentation of the proposed and the structural control of modular multi-level converter that I used for this presentation and this topic. Next, I'll present the proposed fault clearing strategy that I will utilize for this model and this topic. Next is the proposed fault processing schemes, and I'm utilizing a discrete wavelet transform in MATLAB software platform to basically process the fault signals and also extract the features. Next, I'll talk about the protection strategy and the criterion that I used, and the fault classification strategy that I'll utilize. Then I will present the PS-card simulation of the steady state, AC and DC, and also the faulted state of both AC and DC. In addition, I'll present the simulation for half of the load and 2/3 of the load. Then I'll present the DC fault processing scheme in discrete wavelet transform in MATLAB. You basically see all the features and also the entropy and detailed wavelet coefficients. Next is the first item on the outline, and that is the introduction part. As you know, there are a lot of challenges from the current energy sources. And what are the current energy sources that we have? We have coal, oil, gas, and nuclear. As these energy sources produce electrical power, they emit a lot of pollutants into the atmosphere, and basically emit also carbon dioxide into the atmosphere, which basically results in global warming issues. As you know, many nations have put their heads together, and based on the Paris Accord, they have decided that by the year 2030, there should be a net carbon reduction of about 80%, and by the year 2050, there should be a 100% net zero carbon reduction. As such, many nations and many utilities, many investors are looking for alternative means of power production from the traditional means of power production. And what are the alternative means of power production that is out there? We have renewables, which is basically have started penetrating into the power production market. And for the renewables, we have wind farms and solar farms. And out of the renewables that are out there, wind farms have proven to be the best technology as part of the renewable umbrella. For wind farms, we have offshore wind farms. We have onshore wind farms. There's a choice, and the best choice is offshore wind farms. And the reason being that offshore wind farms gives a larger capacity of wind farm to be achieved. Also, due to the larger acreage, larger wind turbines are able to be used. And as you know, technology is increasing day in and day out. Currently, we have research pivoting on 12 megawatts and 14 megawatts offshore wind farms. As such, there's the need to basically exploit the offshore wind farm market. To achieve the larger capacity of wind farm that is needed to export power to the onshore load centers. Out of the technologies that is to be integrated to these offshore wind farms, HVDC schemes and HVDC schemes can be integrated to these offshore wind farms. But there's a limitation when an HVDC scheme is integrated to an offshore wind farms, and the limitation is the distance of cable that is beyond 80 kilometers of submarine cable. There's a problem with charging currents due to the large capacitance of the cable. As such, it requires a reactive power compensation. That is, capacitors has to be installed, which basically drives another cost or embeds another cost into the projects. Also, as the charging current increases and the requirements of reactive capacitors being required, it limits the amount of power that is transferred to the onshore load facilities. As such, the break-even point for offshore cable is 80 kilometers, and sometimes it depends on the amount of power that is being transmitted. That is 80 kilometers and 200 megawatts is a good number or a good estimate to be used to decide on when to use high voltage DC transmission system as compared to high voltage AC transmission system technology to integrate to offshore wind farms. There are two technologies of high voltage DC transmission systems that is out there. We have the current source converters, that is line commutated converters, and we have voltage source converters. But there are advantages and disadvantages of each technology, and we'll talk about it in the upcoming slides. Out of the voltage source converters, modular multi-level converters has been proven to be the technology and topology of choice to integrate to these offshore wind farms because of the many attributes and benefits that outweighs conventional voltage source converters. And if I talk about conventional voltage source converters, I'm talking about the 2-level and the 3-level converters. DC faults can be challenging to interrupt, and I will talk about it in the upcoming slides, why DC faults are very challenging and very difficult to interrupt, and what are the mitigating schemes that is utilized to interrupt DC faults when compared to AC faults. In addition, the processing schemes can also be challenging. As such, that is the need for a hybrid fault processing scheme to be utilized. As such, that is the basis and focus for this research topic, is to come up with a robust fault detection, localization, and classification, utilizing the state-of-the-art technology. Now let's talk about application of this presentation. As you know, many of these offshore wind farms are based in the northeast area of United States, in the North Sea area of Europe, in the Baltic Sea, and most of them are floating turbines, because the sea is very deep. As such, it's very economical to utilize floating turbines compared to fixed bottom turbines. In addition, as you know, there's something they call power to X. That is utilizing the renewable power from these offshore wind farms to produce a green hydrogen through an electrolysis process. In addition, this point-to-point symmetric monopole configuration can be extended to a multi-terminal DC configuration and also a DC grid. And that is the goal of all nations and all utilities by the year 2030 and by the year 2050. Now let's go to the next slide. We'll talk about the current fault detection techniques that we have out there. And the first one is overcurrent protection, which is a non-unit based and localized. Next is undervoltage protection, and that is also non-unit based, and that is based on the change of the DC line voltage compared to the threshold set point. Next is differential protection. Differential protection is a unit based, and that is used as a main protection scheme. Next is the derivatives, and the derivatives are rate of change of voltage and the rate of change of current, and that is a localized protection scheme and non-units based protection scheme. Next is traveling wave, and a traveling wave can be directional wave, and this can be non-unit or unit based, and can be, when it is used as a unit based, is used as a main protection scheme. Next is traveling wave current differential, which also can be non-unit based and unit based, and when it is used as a unit based, it is the main protection scheme utilized. Next, we'll talk about the advantages of the current HVDC fault detection techniques that we have over there. As I made mention in the previous slides, those current fault detection schemes are very simple to implement. Matter of fact, the derivatives, the rate of change of voltage and the rate of change of current is very fast, very high speed, and also has been a mature technology that has been used in the LCC HVDC technology and the voltage source converter technology. They are also very effective. And also the derivatives, that is the rate of change of current and the rate of change of voltage, has some inherent selectivity in it. As you know, the traveling wave does not depend on the magnitude of current, which is basically a great advantage. And as such, it is a very good candidate for high impedance fault. But the caveat is it depends on the degree of the impedance fault, how high the impedance fault is. Now let's talk about the drawbacks with the current HVDC fault detection techniques that we have. They lack the ability to detect high impedance faults. As a matter of fact, these impedance faults are also known as arcing faults. As such, the current magnitudes become so small and so minute that it becomes very difficult to detect these arcing and high impedance faults. Also, for faults that are very close to the MMC converter, it is very difficult for these current fault detection techniques to detect the faults. When there's a fault, we have influence of transmission line and power system parameters, which basically are very dynamic. And this influence makes it very difficult for the current fault detection techniques to detect these DC faults. As you know, when DC faults occur, it has high frequency components, and it becomes a challenge to detect these faults because of the high frequency components of these DC faults. Also, these DC faults are vulnerable to noise, and when it comes to noise, we have background operating noise. And just imagine an industrial facility, substation noise, which basically contaminates these fault signal. In addition, we have other random noise, that is lightning disturbance, that can influence these signals. Also, when you have a short transmission line that is 100 kilometers and below, it becomes a challenge because of the high wavefront velocity. It becomes very difficult to detect that traveling wave fault. It requires a high frequency sampling and synchronization for two terminals. And when it requires high frequency sampling, what does it equate to? It means that it's high cost of protection equipment. Also, because there's a need for time synchronization, especially when you have differential protection where you need to timestamp both ends of the signals being detected and being measured, it results in additional time lag and delay. Also, complex digital processing and computation increases the computational time when you have two terminals or more. As you know, when a fault occurs, it results in traveling wave being generated by the current and the voltage signal. And as this traveling wave propagates from the faulted points towards each end of each converter, the converter acts as an impedance, and basically it results in the traveling wave being directed back to the faulted location through reflection and refraction. As such, due to the impedance of the cable, the traveling wave is attenuated. And this attenuation makes it very difficult to detect these faults. If you have a two-ended scheme, like a point-to-point scheme, and you want to implement differential protection, it requires a reliable communication. This adds to an additional cost and also a delay. And also the communication channel can be vulnerable to failure, and as such can make the protection scheme not reliable. Now let's go to the next slide. Now we'll talk about the current fault processing schemes that we have out there. And some of them are in commercial operation, and some of them are based on literature and research. We have techniques that is based on Fourier transform. and our techniques based on short-time Fourier transform, and our techniques based on Hilbert-1 transformation. We also have techniques that is based on the S transform. The techniques based on the short-time Fourier transform, the Hilbert-1 transform, and the S transform are all based on literature. It is only the Fourier transform that is in commercial operation. We also have the discrete wavelet transform, and that is also based on literature. And actually, that is that one and continuous wavelet transform is what is projecting to be the next technology disruptor for DC protection relay. We also have continuous wavelet transform, and that is also based on literature and research. Hopefully, by the year 2025, there's going to be a protection relay for DC protection based on these processing schemes. Next is artificial neural networks and machine learning and fuzzy logic. Now, let's talk about the drawbacks of the Fourier transform. As much as the Fourier transform is utilized in most of the current protection processing algorithms, it can only process fault transformation in the frequency domain. It lacks the ability to process the fault signal in the time domain, which is basically important to know the time that the fault occurs. Now let's talk about the short-time Fourier transform. The short-time Fourier transform was introduced to mitigate some of the drawbacks that was associated with the Fourier transform. Remember, I made mention that the Fourier transform can only process fault transformation only in the frequency domain, which is not ideal for a DC fault signal. So the short-time Fourier transform was introduced to mitigate the drawbacks that is associated with Fourier transform. But the short-time Fourier transform can only process the fault signal in a smaller window, and even then in a fixed window, though it can process it in the time and frequency domain. As such, the frequency resolution is very limited and can be challenging when it is applied to DC fault processing. Also, it requires more parameters, and also a computational burden in processing all these signals in the algorithm. Like I made mention, the time and frequency information in the signal is limited by the window. Now let's talk about the drawbacks with Hilbert-1 transformation. Like I made mention, these are all based on research and literature, with the hope that by the year 2025 to year 2030, there's going to be a protective relay, DC protection, HVDC protection relay that will be based on these algorithms. Then again, Hilbert-1 transformation also requires more parameters, and if it requires more parameters, that also translates into more computational burden, and also takes longer for the fault to detect, and that won't be ideal for DC protection. It also relies on the instantaneous frequency computation, and as you know, for DC faults, the frequency components are very dynamic. Now let's talk about discrete transform wavelet transform, comparable to continuous wavelet transform. It requires fewer parameters. As such, it requires a smaller computational burden. As such, it is computationally fast, and that is what is required for DC fault detection and processing. It has a fewer coefficients and there's less redundancy when compared to continuous wavelet transform. As you know, continuous wavelet transform results in more coefficients and there's a lot of redundancy, and that itself results in a lot of computational burden and also additional cost. Also, it is very easier to perform the analysis. Next, we'll talk about the current HVDC installations and fault clearing strategies that are out there. What is in commercial operation and also what is based on literature. Currently, we have an installation that is in commercial operation for a 2-level voltage source converter. We have a 3-level voltage source converter and a half-bridge sub-module modular multi-level converter HVDC. There is also a planned hybrid 4-bridge and half-bridge, which is a combination of that configuration that is going to be installed and put into commercial operation. And there's a reason why they are utilizing both technologies. Is to reduce cost and also to reduce switching and conduction losses, and also to lower the cost of installation of these HVDC converters. Also, for asymmetric monopole and bipole configuration, it has also been research papers only. Now let's talk about traditionally how voltage source converters fault clearing strategy that is employed. AC circuit breakers is utilized in a non-selective fault clearing strategies. That is the AC circuit breaker that is located on the AC side of the modular multi-level converter is used to clear the fault in a non-selective way. But that is not ideal if you want to evolve the HVDC configuration from a point-to-point to a multi-terminal DC to a DC grid. Like I made mention, this is the standard practice of fault clearing strategies that is utilized in the current commercial operation of voltage source converters. And matter of fact, even the multi-terminal DC configurations that are out there, is a lot of them that has been installed in commercial operation in China. We have the 3 multi-terminal DC, the 4 and the 5. The reason why the traditional AC circuit breaker is not ideal for multi-terminal DC configuration is because it takes longer for the AC breakers to interrupt the fault, and that is, it takes about 20 milliseconds to about 80 milliseconds for the AC side breaker of the MMC to interrupt the fault. As such, it exposes the power electronics components of the converter to this high peak current and can be very destructive. Though there had been several proposals from other literatures to mitigate these by strengthening this freewheeling diode with other thyristors to prevent it from failing, it's basically introduces additional cost. And also you want to minimize the footprint. Also, the 2-level voltage source converters and the 3-level voltage source converters and the half-bridge sub-module modular multi-level converters lack the fault blocking capability and fault control capability compared to the 4-bridge sub-module MMC. Now, let's move to the next slide. Let's talk about the challenges with DC faults. Why it is very challenging to interrupt and clear DC faults. Because of the smaller resistance of DC cable, and matter of fact, because of DC has a frequency of 0, the reactance is basically 0 or zilch or very low. As such, because of the smaller resistance, DC faults, when it occurs, rises up quickly to about 10 to 14 times the nominal rating current when compared to AC faults. As you know, AC faults has a high impedance and also the X/R ratio of the points where the fault occurs. So the impedance of the faulted point basically minimizes or lowers the fault current. But DC faults does not have that. As such, it results in the very high steep slope and upfront of high current, which can be very devastating for the converter. Also, DC faults do not have a natural zero crossing when compared to AC faults. As you know, AC faults have a zero crossing, and that is the best time for faults to be interrupted without creating any challenges to the fault interruption. But DC faults do not have a natural zero to allow faults to be interrupted easily. As such, it requires a creation of an artificial zero crossing, and we'll talk about it in the coming slides. As you know, there is an increasing and deep penetration of wind and solar energy, which are all inverter-based renewable, into the existing power networks. Also, there is decommissioning of the existing synchronous generators, especially the ones that are coal-fired. As such, this reduces the short circuit levels in the power system network. The inverter-based resources do not contribute inertia to the existing power system network, as comparable to the synchronous generators, traditional synchronous generators, that have larger mass rotors that basically are able to contribute a high inertia to the grid, to stabilize the grid, to prevent the rate of change of frequency decreasing at a fast rate. This reduction of the short circuit levels, because inverter-based resources such as wind and solar do not contribute short circuit and also inertia to the grid, becomes a challenge for the protection schemes that is being implemented for renewables. Now, let's talk about what is the current problems, and that is the statement of the problems that we have with HVDC protection schemes. HVDC protection schemes are vulnerable to DC faults. Matter of fact, the voltage source converters especially. Also, the existing protection schemes that is used in the 2-level and the 3-level cannot be used in the half-bridge submodule MMC. Also, the AC protection schemes, the AC breaker takes about 20 milliseconds to 80 milliseconds to interrupt the fault, which basically results in high peak fault currents being very devastating to the HVDC configuration and can result in the total outage of the HVDC configuration. Also, as HVDC's configuration evolved from point-to-point symmetric monopole configuration to multi-terminal DC grid, and eventually our goal is to achieve a DC grid and super DC grid. The requirement is to achieve a fault interruption time of 2 to 5 milliseconds, and that is a challenge if we continue to utilize the existing protection scheme utilizing AC circuit breakers on the AC side of the converters. Now let's go to statement of problem B, and let's talk about the current fault detection schemes and drawbacks that we have. Like I made mention in the previous slides, right? I listed all the fault detection schemes that we have, the ones that are in commercial operations and the ones that are based on literature. They lack the ability to detect high impedance faults and arcing faults that occur because the current diminishes to the extent that the detection schemes cannot detect these very minute currents. As such, the fault current just stays there and can evolve and propagate into very disastrous faults. Also, transmission line parameters. When the fault occurs, basically, the transmission line parameters becomes dynamic and keeps changing, and it can influence the fault currents. And as such, it becomes very difficult to detect these faults. Also, the high frequency components of these DC faults is very difficult to detect it utilizing the current fault detection schemes. Also, the influence of background and external noise. Background noise means that, like industrial facilities that are close to these substations. And also, external noise being lightning and switching disturbance. Switching from opening and closing of breakers. Now let's talk about the next problem that we have with HVDC. And that is tied to the processing schemes that we have out there. The processing algorithms that we have. Like I made mention, most of the protective relay utilizes a phasor domain, and some of them Fourier transform, but it can process fault signals only in the frequency domain. It cannot process fault signal in the time domain. And with DC fault detection and processing, it requires you to be able to detect the fault and process it both in the time and frequency domain. As such, the Fourier transform becomes a limitation to utilize it for the current schemes and the future schemes that HVDC configuration and topologies are evolving to. The short-time Fourier transform, like I made mention, that it was introduced to mitigate the drawbacks that is associated with Fourier transform. It can process the DC fault signals in the frequency and the time domain, but it's only in a fixed window. And the limitation is that it cannot be applied for DC fault processing because of the dynamic nature and the changing of DC faults when it occurs. As such, a fixed window will not work. Also, distinguishing between lightning disturbance and an actual fault, the current schemes have a limitation on that. And it's very important to have a protective relay that can distinguish between background noise and lightning disturbance in an actual fault, especially HVDC substations that are located on onshore facilities that are exposed to lightning disturbance and also industrial noise or substation noise. So our goal, and the goal for this presentation, is to achieve an effective, robust fault detection, localization, and classification, and the fault clearing strategy that is applicable to a DC cable transmission system that is integrated to an offshore wind farm in a point-to-point voltage source converter HVDC configuration in a symmetric monopole that will be extendable to a multi-terminal DC configuration and eventually to a DC grid and eventually to a super DC grid in the years to come. Now let's talk about the influencing factors of DC fault protection. As much as you put in the robust, the best, the state-of-the-art fault detection, localization, classification schemes, there are influencing factors that needs to be considered when you are implementing these DC fault protection schemes. The first influencing factors is distance. As you go along, or distance increases along the DC cable, the DC fault current basically decreases. So let's consider about 150 kilometers DC cable, and that is the cable distance that I considered for this presentation. The DC fault current that will be seen at 0 kilometers, that is very close, right at the terminal of a converter, will be very high as compared to the DC fault current that will be seen at 20% down the line, that is about 30 kilometers from the onshore converter. Then again, for 50% of the line, that is 75 kilometers from the onshore converter, the DC fault current will decrease. Now let's talk about the selection of our mother wavelet. As you know, there are a lot of mother wavelets out there, and the first one is drawbacks, and the next one is similet, coiflet, and hard. So the choice of the mother wavelet that is used to perform decomposition of these signals is an important factor in designing the protection scheme, and also extracting the features that resembles the original fault signal. Arcing fault is very important, in being considered as part of the protection scheme design. As such, different arcing faults were considered for this protection scheme. Arcing faults of 0 ohms, 5 ohms, 20 ohms, 50 ohms, 75 ohms, and 100 ohms. Matter of fact, there are other literatures that others have considered arcing faults or impedance faults of about 200 ohms. Now let's talk about sampling frequency. Sampling frequency is also very important in the design of a protection scheme for an HVDC scheme. Like I made mention in the previous slide, sampling frequency basically results in high cost of the protective relay. Aside for this research and this presentation topic, I varied the sampling frequency from 20 kilohertz through 100 kilohertz by considering sampling frequency of 20 kilohertz, 30 kilohertz, 40 kilohertz, 50 kilohertz, 60 kilohertz, 80 kilohertz, and 100 kilohertz. And matter of fact, there are literatures that can go all the way up to 5 kilohertz or 10 kilohertz. The goal is basically to prove that at a much lower, very low sampling frequency, still the features of these fault signals can be extracted, and also the fault level decomposition can also be achieved correctly, which results in lowering of cost and also decrease of computational time for these protected relays. Lightning disturbance. Okay, as you know, if you look at the topology of these schemes, right, we have an onshore converter, MMC converter, and an offshore MMC converter. The offshore MMC converter is located inside the building on the platform, substation platform, whilst the onshore substation is outdoor. It's basically an air insulated substation. As such, it's vulnerable to lightning disturbance. So very important that we consider lightning disturbance as part of this presentation for the single line to ground fault, and also three-phase bolted fault on the AC side of this MMC converter. Now let's talk about background operating Gaussian noise. Within an HVDC substation or any other substation, there's an operating background noise. And matter of fact, if the substation is located close to an industrial facility, the noise background noise even becomes higher. As such, Gaussian noise ranging from 5 dB, 10 dB, 20 dB, 30 dB, 40 dB, 50 dB, and 6 dB was considered and was added to the signals, to the steady state signals and also the faulted signals before processing was done. Now, let's talk about what is a high voltage DC transmission system. It can be defined as a point-to-point or a multi-terminal DC configuration. That is, if you have more than 2 terminals, 3, 4, 5, is considered a multi-terminal DC. And when many multi-terminal DC are integrated, it forms a DC grid. And also when many DC grids in different countries are interconnected, it forms the super DC grid. And that is the goal of the future. By the year 2030 and 2050, the goal is to achieve a super DC grid. When it utilizes converters to convert the AC power that has been generated to a DC utilizing a rectifier station or rectifier converter, and when another inverter converts the DC power to an AC equivalent before it is transmitted back to the grid. Within the HVDC, as you know, the goal is to achieve a multi-terminal DC grid and also a DC grid in the future, and super DC grid in the future. We can utilize a DC to DC converter that can step up or down the DC voltage, and that helps us to achieve a multi-terminal DC or a DC grid. And there's still ongoing research on DC to DC grid, and hopefully it will come into realization and commercialization very soon. HVDC is very efficient and it's an alternative means of transmitting large amount of and bulk amount of electricity over long distances. And basically that is what is utilized in China, where all the hydro generating stations are located in the northeast area of China. And basically to get the power transmitted to the load centers that are located in the south area, HVDC is utilized. Now let's talk about the application of HVDC. HVDC can be integrated to wind farms. And like I made mention, it is the best technology to integrate to these offshore wind farms that are located in very remote location to harvest the power and transmit it to the city center where the load centers are located. So below is a picture of one of the wind farms, the Baldwin wind farm, and that is located in Germany. And the rating is 400 megawatts with a DC transmission voltage of pole to ground of 150 kilovolts plus or minus, and pole to pole of 300 kilovolts. And the onshore cable or AC side export cable is 75 kilometers, whilst the DC export cable is 125 kilometers. So as you can see in the picture, that's a typical picture of an offshore substation platform where all the equipment are located. Also, HVDC can be applicable to island power generation, where you can have an embedded generation of solar, wind, battery energy storage system, which can either be connected to the grid or operate as an island power generation. It can be utilized in a multi-terminal DC configuration, and a multi-terminal DC configuration means that you have more than 2 terminals. And currently we have the 3-terminal, the 4-terminal, and the 5-terminal, and they are all in China. Also DC grid. Like I made mention that if you have a multi-terminal DC grid, which involves more than 3, 4, 5 terminals, you can connect many multi-terminal DC to form a DC grid, and many DC grid to form a super DC grid. Also, as you know, some of the cities can be choked in terms of having space. And as you know, demand of power is increasing on a daily basis. And because some of these city centers are choked, it's very difficult to basically construct and install a conventional power plants in these centers. So HVDC technology becomes the ultimate choice because of this very smaller footprints to install to provide voltage and power to this city center's load. Next is moving more or large power over very long distances in between transmission corridors, that is between nations. Like I made mention that moving large amount of power over long distances, that is basically what is utilized in China, where a lot of the hydro power plants are located in the northeast area, and 6,000, 8,000 kilometers of DC transmission lines are integrated to these generation facilities to the load centers that are located in the south area. And also between transmission corridors, that is a back-to-back HVDC is utilized to basically integrate asynchronous generation and transmission system, that is between nations that are utilizing different frequencies like 50 hertz and 60 hertz. and that is a typical example that is utilized in Argentina and Brazil. Now let's talk about the timeline for the evolution of high voltage DC transmission system. We're not going to go into the earlier part, the DC war between Edison and Westinghouse, but we'll basically start from 1954, where the first HVDC commercial operation took place in Gotland, in Sweden. Then in 1965, basically it moved to New Zealand, where the first HVDC was also installed there. But those HVDC technologies were the mercury valves. But the first thyristor valve was basically 1972, and I think that was the Nelson River, if I recollect. And in 1980, basically, computers were introduced to control the HVDC. Then, in 1999, basically, technology evolved. The line commutated converters, which has been the traditional or conventional classical technology, which has been the most mature technology. There was another technology called a voltage source converter, and the first installation was in 1999, and that was installed in Gotland, Sweden. The same technology was installed in Australia in 2000. As you know, like I made mention that we have many topologies or technologies of our voltage source converters, and that is the 2-level, the 3-level, and also the MMC modular multi-level converters was introduced to mitigate the drawbacks that is associated with this traditional or conventional voltage source converters because of the many attributes that it has. And I will talk about the attributes in the next coming slides. So the first modular multi-level converters was installed in 2010. And basically there was a limitation on the DC transmission voltage. So around that time it was plus or minus 150 kV. Then basically it evolved to about 320 kV. For current source converters, basically line commutated converters, technology has helped, and basically now they're looking at ultra high voltage DC transmission, and they're looking at 1100 kV and about 8,000 kilometers and 10 gigawatts of power being transmitted. Now let's talk about comparison between HVAC and HVDC, and why the choice of HVDC. In HVDC, there's no reactive power loss and transmission losses. The reason being that it's only resistance of the cable that is being considered, because the frequency is zero. It's the frequency that is zero, and so as such that the impedance is zero, and that also results in lower transmission losses. Next is lower transmission cost and fewer conductors. As you can see the picture on the right side, right, there are fewer conductors. There are only 2 conductors when compared to the AC counterpart that has 3 conductors. As such, that results in lower transmission cost. HVDC can be integrated to 2 non-synchronized networks. Remember, I made mention that you can have a transmission frequency of generation and frequency of about 50 hertz, and you can have another country that is having 60 hertz. To be able to transmit and integrate to these two nations, you need an HVDC back-to-back network that will basically integrate the 50 hertz and the 60 hertz different frequencies and be able to exchange power between these two nations. It is able to transmit power for longer lengths of underground cable, submarine cable, and transmission lines. There is no charging current as compared to HVAC. For high voltage AC transmission system, cabling system, because of the high capacitance of the cable, there's a lot of charging current, and it requires a lot of charging power to be able to charge that amount of charging current, and also it requires a reactive power compensation for that. But for HVDC, there's no charging current as such that translates into savings. As you know, for HVAC, when you have a network fault, it can result in stability, especially with the rate of change of frequency. It can change so fast that it can be a problem. But for HVDC, there's no problem like that because of the converters have the ability to basically exchange power in both directions and also provide support to the grid when needed. As such, there's no stability problem. For HVDC, there's no skin effect. In HVAC, because of the frequency as such, the cross-sectional area of the conductor at times is not utilized, and basically the current flows on the peripheral surface of the conductor instead of taking the whole section of the conductor. But for HVDC, there's nothing like that. And also for light loads for HVAC, there's something they call variability effect, where the voltage on the load end increases very high. With HVDC, there's no problem like that. HVDC requires less spacing footprint as compared to AC transmission system of the same voltage rating. The reason being that because of the additional spacing that is required for the reactive power compensating devices, etc. Also, there's less coronal and interference as compared to HVAC. Also, there's no reactive compensation, even at high voltages as compared to AC network. It has much stability, much more reliability, and power reversal. Like I made mention that power can be exchanged in both directions. Now let's talk about the disadvantages of high voltage DC transmission system when compared to high voltage AC transmission system. The terminal cost can be very high. But if you break it down, basically it pays off as with time, based on continuous operation of the HVDC scheme. Because of the power electronics of these converters, right, it introduces harmonics. As such, especially for current source converters, like line commutated converters, right, it introduces harmonics and it requires filters. And these filters introduce additional footprints and also basically additional costs. Also, there's limited overload capability. Matter of fact, The current source converters can be overloaded a little bit, but for the voltage source converters, it's basically, there's no way you can overload it. So it lacks the overload capability. Also, the current source converters, when connected to a weak grid, basically it becomes problematic, and it can result in commutation failures, especially the inverter side of converter. Yeah. Also, the current source converters requires reactive power. As such, basically, reactive components have to be installed, as capacitance has to be installed, and which basically introduces additional cost. I think I made mention of about commutation failures for the inverter side line commutated converters, and basically that can be very problematic. Also, current source converters requires strong voltage or stiff grid, So basically, that itself introduces additional cost, in making it performing all the feasibility analysis to make sure that you have a strong grid to integrate it to. Okay, now let's talk about when do you decide on HVDC as compared to HVAC, and that is very important, So as you can see, the graph over here, I have on the vertical axis scheme cost, right? So for AC station and a DC converter station, and on the horizontal axis is the transmission distance, right? Okay, so as you can see, for cost, AC station it's much lower than DC converter station. But like I told you that, with time, basically it after the break-even distance, it becomes cheaper, if you implement DC converter stations at, based on the break-even distance. So for overhead line, the break-even distance is 800 kilometers. And for submarine cable, it's about 50 kilometers. And for underground cable, similarly, about 50 to 80 kilometers. Now let's talk about the types of HVDC configurations that we have out there. We have the monopole configuration, which can be either symmetric monopole or asymmetric monopole. We can have the bipolar configuration. We can have the back-to-back. I think I made mention of the back-to-back in the previous slides being utilized to integrate asynchronous transmission and generation networks. That is a network that has 50 hertz, and if another country has 50 hertz, another country has 60 hertz. Basically, you utilize back-to-back configuration to integrate these generation transmission networks. Then we have the multi-terminal DC configuration. So as you can see over here, I have a picture of basically how the symmetric monopole configuration looks like. Basically, it has a positive pole and a negative pole, and basically both poles are rated the same, and basically, same costs. So that itself, symmetric monopole is more costlier than the asymmetric monopole, because the asymmetric monopole, basically, you have only one pole, and the return can either be ground return or metallic return. So that is why it's called asymmetric, because both poles are not similar. Then we have the bipole configuration, which basically has two terminals on each side, and has both a positive and a negative pole, and in between we have the neutral that is grounded on each end. Then we have the rigid pole, right? Basically that has switches that allows us to basically switch the converters. And for the multi-terminal DC configuration, we can have a series and parallel in a meshed configuration. Okay, so Next is a picture of how a multi-terminal DC configuration looks like. As you can see over here, we have a 3-terminal on that side and also another 5-terminal. Okay, so 1, 2, 3, 4, 5 on the left side. On the right side is a 3-terminal, on the left side is a 5-terminal. So that is what we call a multi-terminal DC configuration. Okay, so now let's talk about the different types of HVDC configuration. I've made mention of it in the previous 2 slides. I've shown you pictures of it, how they look like. Now let's talk about the pros and cons of each. For symmetric monopole, there's no DC for current flow, right? Because you have the positive and the negative pole. There's no return for unbalanced current. It requires smaller cables, and it utilizes standard AC transformers, which can be very convenient and much cheaper compared to converted transformers. Because converted transformers, the insulation systems has to be designed for AC and DC bias, which basically introduces additional cost. But the disadvantages or the cons is that there's no redundancy. That is, if you have a faulted pole, basically it results in 100% loss of the HVDC configuration. Okay, and also there's an increased cost if compared to asymmetric monopole, because it requires 2 HVDC cables and poles that should be fully rated, and also it requires higher power losses. For asymmetric monopole, which is basically the most basic, it has a lower cost. The pros are compared to symmetric monopole and bipole, because it has only one conductor, and the other conductor is a metallic return, and also there's no DC ground current. Also, the ground current has a lower voltage. And metallic return is basically rated at a much lower voltage, which basically introduces 2 additional costs. On the cons, there's no redundancy, just like the symmetric monopole. For the bipole, there's no DC ground current flow. There's no path for it, And also you have redundancy, inherent redundancy in it. That is, if you lose a pole, basically you can operate the other pole utilizing basically it shifts from a bipole configuration to a symmetric monopole configuration. The cons are it has a higher cost. Okay, for rigid bipole, similarly, there's no DC ground current. And you don't have, there's no need for metallic return and electrodes. That is utilized in asymmetric monopole configuration. And also you have inherent redundancy in it, and also you can have a double capacity, just like the bipole configuration, On the contrary, on the con side, it requires high-speed switches in the substation or the switchyard, and basically that can to be able to switch, fast, when you have converter faults to the converters that do not have faults. But these high-speed switches results in high cost. Now let's talk about the different types of HVDC technologies we have. Remember, I made mention in the very first slide for the introduction. I made mention that we have 2 technologies for HVDC. That is the line commutated converters, which is a current source based converter, and a voltage source converter, which is basically voltage based. Okay. So now let's talk about the line commutated converter. This has been a very mature technology and has been around since the 1950s. Very reliable. It is a thyristor based, so it means that It utilizes a thyristor for commutation and also for conversion from AC to DC and from DC to AC. It is known as the very classical or conventional based technology. It has a lower converter power losses when compared to the voltage source converter, and has a higher transmission power capability. Remember, I made mention that in China they have an ultra high HVDC transmission system that is rated at plus or minus 1100 kV, right? Okay, that utilizes a current source converter technology, yeah, and is able to transmit large power, about 10 gigawatts over about 7,000 to 8,000 kilometers, all the way from northeastern part of China to the south area where the load centers are located. An inductor is used on the DC side, and that's a larger size of inductor to basically mitigate, and limit the high rise of fault currents. Also, the inductor helps to achieve a constant current source. It is more tolerant to faults when compared to the voltage source converter. The reason being that you have the larger inductor on the DC side that is able to mitigate and lower the high peak of the fault currents. And also you have the thyristors that are able to be controlled to basically extinguish the fault current. On a footprint basis, it is larger, when compared to the voltage source converters, because of additional equipment that is required, filters, and also reactive power compensation devices. And also it is more expensive. It requires a relative strong grade. And what does it mean? It means that it requires a grade that it has a high short circuit capability and a high short circuit ratio. Like I made mention that basically the current source converter, it requires a reactive power compensation. Matter of fact, the valves alone requires about 60% of the power that is being exported, and also capacitors and filters also has to be installed. I think I made mention of this current configuration that we have, basically the ultra high HVDC configuration that is located in China. Has a larger footprint. For current source converters, line commutated converters, there's limitation, below 90% of the rating, or 10% of the rating, it cannot operate. Now let's pivot on voltage source converters. Voltage source converters are IGBT based. And what is IGBT? What does it mean? Insulated gate bipolar transformer. It is self-commutating. That is basically it can turn on and off through control action by itself. It has a capacitor that is used on the DC side. Compared to the current source converter, the line commutated converter features an inductor. But for the voltage source converter, it has a capacitor that is located on the DC side to basically maintain and make sure that the voltage is at the right threshold. Its goal is basically to ensure there's a constant voltage, as compared to the current source converter that ensures that there's constant current. It allows black start, and what does it mean? It means that it can provide its own voltage, because that is the reason why it is used in city load centers, basically because of its capability to provide that it synthesizes its own voltage. It is less, fault tolerant, in that it is very vulnerable to faults as compared to current source converters. It is smaller in footprint because the reactive compensation devices that is required by the current source converters is not required here. And sometimes, filters might not be, depending on the level or the technology or the topology type, filters might not be needed. Also, it has a higher switching and conduction losses compared to current source converters. Now let's talk about the different topologies of voltage source converters. In the previous slide, we talked about the different configurations of HVDCs that we have over there. We have the current source converters, the line commutated converters, and we have the voltage source converters. Now, this slide, we are talking about the different topologies of voltage source converters that we have. We have the conventional two-level topology. We have the three-level topology, and multi-level converter. And the reason why the multi-level converter approach was introduced is basically to reduce, the dVdt, because of the distribution of voltage, and also to lower the switching and conduction losses. Because, for the multi-level converters, we are utilizing a lower frequency for switching, whilst in the two-level and the three-level, we are utilizing about 1 to 2 kilohertz. And whilst multi-level converters are typically, about 250 hertz or 125 hertz can be used. And that translates into a lower switching frequency losses. Also, the harmonic distortion is reduced, which basically eliminates the need for filters and introduce cost savings. Now let's talk about the advantages. Also, the investment cost increases based on complexity. Okay, actually, this one is a disadvantage, because as investment cost increases, also there's complexity in the controls as well. Also, it requires extensive capacitor balancing algorithm. Now, let's talk about the advantages of voltage source converters. Voltage source converters has the ability and capability for both active and reactive power to be controlled independently. It does not require reactive power compensation as compared to current source converters. It has a faster response, and also power restoration is very fast when a blackout occurs because of the fast response utilizing the IGBTs, insulated gate bipolar transistors. It can easily be connected to a weak grid. As compared to line commutated converters or current source converters, it becomes problematic if it is connected to a weak grid. It means that additional reactive compensation devices has to be installed at the point of interconnection. That is the STATCOM, or capacitors has to be installed at the point of common coupling for it to work efficiently. It can be connected and integrated to remote offshore wind facilities. It is very compact and has a smaller footprint because no capacitors are needed, and also less or harmonics, and also which translates into less no voltage required. Compared to line commutated converters, voltage source converters utilizes ordinary power transformers, which basically introduces cost, which introduces to a lower cost savings. Also, power reversal can be achieved easily compared to line commutated converters. For line commutated converters or current source converters, basically physically the polarities of the cables has to be physically changed before power reversal can be achieved. Compared to voltage source converters, it can be done through controls. Next, it can provide power to a passive network. And what does it mean? Those are load centers. Basically, it's because it's able to provide that amount of power easily. You can utilize it in these load centers and provide power to those city centers. Now, This is a picture of how a scheme looks for the multi-modular converter. As you can see over here, right, we have this area is called the upper arm, and below that is the lower arm. And within each of these are sub-modules, which has been connected in series, right? And for this one, as an example, we are utilizing a half-bridge sub-module. So as you can see, we can have thousands of these half-bridge sub-modules that has been connected in series or cascaded in series to basically achieve the required voltage that is needed. Then we have basically the phase reactor, right? And what is the purpose of this phase reactor? Is basically it helps to achieve the amount of power exchange that is between the converter and the AC grid. Then within the converter, we have this reactor that basically, the arm reactors basically, that helps to limit the amount of fault current that flows when there's a fault. Now let's talk about the power transfer equation, right? Okay, so as you can see over here, these are the active power transfer equation and the reactive power transfer equation, right? So the UL is the voltage that is on the grid side, right? And UV is the voltage that is synthesized on the converter side, right? In between is the converter transformer. So basically the leakage reactance and the leakage inductance of the transformer is able to effect and make it possible to basically transfer active power and basically reactive power between the grid and the converter. Next, we'll talk about the components of a voltage source converter, HVDC, right? So as you can see over here, we have a typical substation, an HVDC substation, and as you can see over here, the AC transmission line comes in, and this is the AC switchyard, and these are all shunt capacitors that is basically utilized to basically provide a reactive compensation. And also we have harmonic filters. Remember, I made mention that these power electronics converters basically produces harmonics and when it operates. So you require harmonic filters to basically filter all these harmonics. Then you have a converter transformer on this side, basically that is able to provide galvanic isolation and also effect the required voltage that is required by these valves that are located in the valve hall. So the valve hall basically is what the converters are located. So the AC voltage is converted to a DC, and from here it goes to a DC line. Below that is actually a schematic of how it looks like. So basically this is the AC bus over here. So this is all the AC buses here that you see over here, and this is the AC filter, and different filters are tuned, singly tuned filters, and this is the converter transformer, and this is the converter. So on the DC side, it also has DC filters as well, and also snubbers and metal oxide arresters as well. Okay, so now let's talk about talking about the components of the voltage source converters. We have valves, right? Remember, so the valves are located here, and the valves are the converters themselves. Then we have the converter transformer. The converter transformer is located right here. And what did I say about the converter transformer? The converter transformer is basically, it provides galvanic isolation between the AC and the DC side, and also it's able to provide the required voltage that is required by this converter to basically produce the required threshold design rated DC voltage that is needed. Then we have the reactor. So the reactor basically, it's the one basically that helps in addition to the leakage reactance of the transformer, is the one that helps basically to effect the power exchange, active and reactive power exchange between the converter and the AC grid. Next is harmonic filters. as you can see over here, the filters are located over here, and the reactive capacitors are for reactive compensations are located here. So, as I made mention, the converters basically provide harmonics when they are in operation. So when they are produce the harmonics, basically require filters to basically remove these harmonics. Then you have a transmission line and cables. Okay, so the AC transmission line coming in here, then DC transmission line cable, transmission line also on this side. For the converter transformer, what are its purpose? Remember, I made mention that the converter transformer basically provides galvanic isolation, that is from the AC side and the DC side. And also the required voltages that is to be used by the converter to produce the required DC voltage that is needed. It also acts as a fault limiting impedance. Remember, the transformer, the converter transformer has a leakage reactance. So it utilizes the leakage reactance to limit the AC side fault. Also, it provides the required phase shift. Usually, some of these converter transformers for a voltage source converter, you can have a Y ground and a delta on delta configuration on the MMC side. Then a reactor, I made mention, limits the fault current on the AC side. And also harmonic filters basically removes all the harmonics that are produced by the power electronics converters. Okay, so next are pictures basically that shows you the components of the HVDC cable, right? And this is a typical HVDC transmission line. As you can see, this is the positive and this is the negative. Next is a typical converter. So inside a valve hole, this is how the converters look like. So this is a typical plus or negative 320 kV voltage source converter. So with a pole to ground voltage of 320 kV and pole to pole voltage of 640 kV. So this one is a voltage source converter utilizing an IGBT, insulated gate bipolar transformer. On this side is basically a line commutated converter. Basically it utilizes triodistors. This side is basically capacitors that are utilized for reactive power compensation. Now let's talk about MMC, modular multi-level converter. Remember, I may mention that this is basically the latest generation. I think that is the 4th generation of voltage source converter. So there are two known topologies that we have. We have the half bridge and the full bridge. Right? So for this presentation, I'm utilizing the half bridge, and that is the trade-off between utilizing the half bridge compared to the full bridge. The trade-off being that the half bridge has a smaller number of IGBT switches. That is, it has 2 IGBT switches compared to the full bridge that has 4 IGBT switches. So as such, it has a lower switching and conduction losses. Also, the cost compared to a full bridge is much lower. On the other hand, the caveat is, the half bridge lacks fault blocking capability compared to the full bridge that has a full fault blocking capability and fault control capability. As such, if I'm utilizing the half bridge submodule for HVDC protection scheme, I will need a DC breaker on each end. On the other hand, if I were to have utilized a full bridge submodule converter, then I wouldn't need a DC breaker because the full bridge submodule has that capability of basically blocking the fault current and controlling it to 0. So on the DC transmission side, all that I need will be high-speed switches, which basically translates into lesser cost. Okay, so now let's talk about the advantages of modular multi-level converter, MMC. Okay, the capacitors are distributed. Remember, I told you that they are a sub-module, right? And basically, you can have thousands of them. You can have hundreds of them that are basically connected in series to whatever voltage that you want to achieve. So the capacitors are much more distributed compared to the 2 and the 3 level, where you have a large capacitor, right? So the 2 and the 3 level, like I did mention, that you have a very large capacitor. It means that when a fault occurs on the DC bus or the DC cable, it leads to a large fault current and larger transients, compared to these distributed capacitors, where the fault current levels can be lower. Ease of scalability. That is, you can add additional models as you need, to achieve, the required voltage that you need, And as you add more levels or more modules, basically you approach a perfect sinusoidal wave. It has a low or very zero harmonic filters, depending on the amount of series connection of sub-modules that you have. So now let's talk about how it operates. So you have basically IGBT on top, right, and IGBT at the bottom. Only 2 IGBTs, for the half-bridge sub-module. The full-bridge sub-module has 4. So you have the IGBT transistor and basically the freewheeling diode. Right? Okay, so when the current is flowing in this direction, what it is doing is fully charging the sub-module capacitor. Right? Remember, I told you that you could have hundreds, thousands of these, depending on the desired voltage that you like and your design. Right? So when the current is flowing on this direction, is fully charging this sub-module capacitor. Right. On the other hand, if the current is flowing in the other direction, then that is considered discharging. So this one is charging, and on this side is discharging. And discharging occurs when there's a fault. Charging is basically, during energization of the converter. Then next is bypass mode. You can also have bypass mode, where basically you bypass the sub-module capacitor. So basically you can have a bypass mode where basically you bypass through the IGBT, right? On the other hand, if based on the current direction, you can bypass the sub-module capacitor, and so these are all the operating modes of the half-bridge sub-module. Now let's talk about the control scheme for the voltage source converter, right? This is the general control scheme that we have for the voltage source converter. Okay, so you have a voltage source converter here, and you have a voltage source converter over here. Okay, so let's say one is operating as a rectifier and the other one is operating as an inverter, right? Okay, so you can have a AC voltage control and reactive power control over here, and have a DC voltage control and active power control. So basically, utilizing these controls, basically that becomes your outer level control, right? And based on your dispatch level, right, you basically determine your direct axis and the quadrature axis currents, and based on the type of control scheme that you have designated. You remember, okay, let's say if we choose AC voltage control and reactive power control on this side, the goal is basically to control in the inner loop, the quadrature axis to control the reactive power to achieve the required voltage that is on the side. On the other hand, if we choose a DC voltage control on the side and active power control, then the goal is to basically control the direct access current so that we can control the DC voltage on this link to be able to achieve the required active power output. So this is a picture that shows how the inner controls looks like the DQ controller. So we have an outer controller, and it can either be AC voltage or reactive power, or DC voltage and active power, which is basically, becomes your outer control loop, and your inner loop are basically the current-based control loops. That is your direct axis and the quadrature axis. So basically, utilizing the pulse width modulation, basically, it provides the switching signals to these converters to basically operate the converter. So next is basically how a vertical axis and a horizontal axis wind turbine looks like. So as you can see over here, this is a horizontal axis wind turbine, and this is a wind turbine that is located at I think one of the northeast coast cities. Okay, so next is horizontal axis wind turbine, and this is an onshore wind turbine, and this is basically offshore wind turbine, and like I mentioned, these are horizontal axis wind turbine. Now let's talk about the power curve for a wind turbine. Right. Okay, so as you can see, the power curve is based. The power for a wind turbine is based on the density of the wind and the swept area of the wind turbine blades and the volume, the velocity of the wind speed or the wind speed, right? So that is basically the power that is generated. Okay, so there's something they call current speed, right? Okay, so as you can see over here, there's a current speed before the wind turbine blades even start spinning. So let's say if the current speed is about 4 meters per second for the wind, so once the wind speed being sensed by the wind vane or the the anemometer, then basically the power basically cuts in and basically start generating power based on the cubic velocity of the wind based on this curve. So as the cut in speed increases and the power increases, it reaches the rated power, right? So this is the rated power that is captured. So when it reaches the rated power, basically then it stays there and basically generates, it locks in and basically provides the required power that is required to be exported by each wind turbine. And there's something they call a cutoff speed, right? Okay, so cutoff speed, what does it mean? Let's say you have a wind gust, excessive wind speed, below, above, let's say 20 meters per second, and the rated speed, wind speed can be about 11-12 meters per second, just to mention of that. The current speed can be about 4 meters per second, and the rated speed can be about 11-12 meters per second, and the cutoff can be about 20 meters per second. So at this time, when the wind speed has increased so much, it can be very dangerous for the wind turbine. So what it does is, basically, there's this, basically, it takes the wind turbine out and basically, put it to a stop. Now let's talk about the types of wind turbines that we have over there. We have about 4 wind turbines. Types of wind turbines, that is type A or type 1, type B or type 2, type C or type 3, type D or type 4. Right? Okay, so let's talk about the type A, which has been in it's been in existence for a longer time. Actually, the evolution of a wind turbine started from that. And I'm pretty much sure, the different types of wind turbine, the vertical speed and vertical and the horizontal also evolved from that. So this one is just a conventional squirrel cage induction generator. So the wind turbine is connected to the AC grid, and through a step-up transformer. So for this one, the frequency of the grid is the one that detects the speed of the wind turbine. And it requires a reactive power support because it's an induction generator, right? Basically, it requires reactive power, and that has to be installed at a point of common coupling. Next is it is very simple, and very robust in construction, and it requires a strong grid. So if you have a weak grid, then basically you have to install a STATCOM, SVC, or reactive power compensation at the point of common coupling. The cost is lower. Actually, it's one of the cheapest wind turbines that you have. When you energize this wind turbine, it basically results in a high inrush of large starting current. And that also needs to be taken a look at. And the power conversion is very low. Efficiency is very low. And basically, when there are changes in the wind speed, it doesn't change the speed of the wind turbine because, like I made mention, the frequency of the grid is what dictates the speed of the rotor. It also results in excessive mechanical stress and fluctuation. Now let's talk about the type B wind turbine. And basically this one allows you some flexibility and some latitude of some variable speed up to about 10%, plus or minus 10%. And this is one rotor that basically has an embedded variable resistance. So the variable resistance is what basically allows you to operate, vary the speed of this wind turbine. And just like the type A, it also requires capacitor bank. And also it has an embedded soft starter that basically allows you to gently start it, limiting the inrush. As you can see, the soft starter over here, that's what allows you to basically limit the inrush. So now let's talk about it basically has much energy conversion efficiency higher than the type A, and also it reduces the mechanical stresses as compared to the type A that is due to wind gust. It allows basically variable speed and slip control up to about 10%. And also because of the soft start that is used to bring it up to speed during starting, it reduces the wear and tear and also the gearbox maintenance. It has like I mentioned, the variable resistors that are embedded in the rotor winding that allows you to basically vary the resistance of the rotor as such that control the speed of the wind turbine. It also requires a reactive power and a gearbox. So next is type 3 wind turbine, and that is a double fed induction generator. Okay, so as you can see over here, this is basically a picture of it, and that shows the blade, and basically low shaft speed, the gearbox. The low shaft speed from the blade is coupled to the gearbox. And the purpose of the gearbox is basically to multiply the speed. Let's say you have a wind turbine blade that is spinning at 17 meters per second. Then if it is coupled to this gear system, basically it can enhance and multiply the speed to faster revolution to about 1,000. And from there you have the generator and also a controller and anemometer and speed sensor. So the housing is called a nacelle, and here is the high speed shaft, and over here is the low speed shaft. So this is the braking scheme that allows you to brake it if you have excessive wind gust, and your drive which has a motor that allows you the wind turbine blades basically to point, to redirect in the direction if the wind direction also changes. And below that is the tower, long tower that goes. Yeah. Okay, so now let's talk about the advantages of the wind turbine. Like I made mention, the type A has a limited speed control, very, very limited, and type B allows you a little bit of speed control, variable speed control. But the type C, the type 3 basically gives you more flexibility and allows, plus or minus 30% speed control, and has the capability of, decoupling, allows active and reactive power control. And also the power converter is rated at 30%, which basically translates into cost savings. Now let's talk about the disadvantages. Because of the gear system, right, and also the slip rings for the brushes, right, it requires a lot of maintenance, and the maintenance can be very expensive. So actually, that is the drawback why the type 3 cannot be used at offshore facilities, because that is very, very remote facility, and because of the salt, the sea salt, basically it can basically result in a lot of deposits on this gearbox system and slip rings, and which basically can require a lot of maintenance and also breakdown of this wind turbine. As such, the type 3 is mostly used in onshore facilities. It is subject to frequent faults, and equipped with rotor current controllers. Basically, you have two converters, machine side or rotor converter, or grid side converter. Grid side, converters that basically that allows the rotor control of the speed of the rotor current. It is aerodynamically efficient. What does it mean? That because of the power electronics that is utilized to control this wind turbine, it makes it very aerodynamically efficient. Also, the variable frequency voltage that is applied to the rotor basically allows two rotor currents, and that is in the direct axis and the quadrature axis, and also the control of the speed of the rotor. Okay, now with regards to the control, right, we have a rotating reference scheme that is basically synchronous scheme that is basically projected and basically converted into DQ quantities, and that is DC quantities from AC quantities. Then that is basically what the control schemes is. That is direct axis and quadrature axis. So based on the flux-based control scheme, changes in the direct axis current basically results in changes in the reactive power control. And changes in the quadrature axis basically results in changes in the active power control. So this is a picture of how the double-fed induction generator looks like. Okay, so as you can see over here, it has a different operation. It has over synchronous, synchronous, and asynchronous. Okay, so over synchronous is basically when the stator is exchanging power with the grid, and the rotor also is exchanging power with the grid. And synchronous is only when the stator is exchanging power with the grid, and the rotor is actually taking the power that is from the stator back to the rotor. So as you can see over here, we have the rotor side converter, right, or the machine side converter, and on this side we have the grid side converter. In between is a DC link and a capacitor, a storage capacitor, and basically these are connected back to back. So and this is integrated to the control system. So we have the turbine blade, that is where the wind direction, wind speed hits the turbine blade and it rotates, and we have the gearbox scheme, and we have the the low speed shaft that is connected to the low speed shaft right here, and the high speed shaft when it goes through the gear system, and that is integrated to the rotor, and we have the stator that is integrated to the grid. Okay, so now let's talk about the components. Like I've made mention previously, I've shown you a schematic of how the wind turbine, especially the Type 3 wind turbine, how it looks like. Okay, so this is how the wind turbine inside the wind turbine looks like. Also, as you can see over here, this is basically a braking scheme that is connected to the gearbox over here, right? And then from the gearbox is connected to the generator, and this is the picture of how the gearbox looks like, and this is a picture of how the gear system internally looks like. Okay, so if you have a wind farm, wind turbine that is in operation, right, and you can see as you have the wind direction moving in this direction, and let's say if you have the wind direction changes, right? Okay, so you have speed sensors, wind direction speed sensors over here, velocity sensors that are over here. That senses the direction of the wind. So this is integrated to a controls, and the controls are integrated to the motor of the yaw system. And these are the motors of the yaw system, which basically turns the wind turbine in the new direction where the wind velocity is flowing and the new wind direction is flowing. Okay, so many of you that you have not seen how a wind turbine blade looks like. This how the size of a wind turbine, and as you can see over here, it is being carried by 2 trucks. That's how they transport this. And this, matter of fact, for onshore wind farms where the megawatt rating is between 2.3 to about a little bit over about 3 point something, let's say about 3.5 megawatts. The turbine blades can extend to about 85 meters. Yeah. But for offshore wind farm, it can be longer than that, because offshore wind farms that is where we have a higher wind turbine rating. And basically those can go over 150 meters. Okay, so inside the wind turbine, right? Remember I told you that the vertical part of the wind turbine from the top, it comes all the way down. As you can see over here, comes all the way down. So inside this tower, these elevators, that helps people that are working on the wind turbine to move from the bottom to the top. Basically the bottom part is where the converters are located, and the breakers are located, and so that shows you a lift, somebody moving from the bottom of the wind turbine to the top to work on the wind turbine. And okay, and this is a picture of how the wind vane and windmills are installed. Okay, so next is a picture of how the yaw motors. Remember, I told you that the yaw motors are the ones that redirect the wind turbine blades, and basically, based on sensing from the velocity sensors that are installed at the back of the wind turbine, and this is basically the gear system, and this one is basically the step-up transformer. As you know, this wind turbine basically has an output voltage of about 690 volts, right? So it is basically connected to this step-up transformer, and this step-up transformer steps the voltage to a collection level of let's say 33 kV, and these days they are moving to a 66 kV collection point, AC collection point. So this is basically for onshore facilities, it steps the voltage from 690 volts to 33 kV or 66 kV. But for offshore facilities, definitely you cannot have this power mounted transformer will definitely be located at the bottom of the tower. That's where they are located. But technology has improved so much that these days I think they have a wind turbine that they have these power mounted transformers, matter of fact, located on top of the wind turbine, and also switchgears 66 kV GIS switchgears that are located on top of the wind turbine. Okay, so now let's talk about the type 3 wind turbine protection. That is localized protection for the wind turbine. So as you can see, when there's a fault, right, be it wind farm side fault, it results in basically the rotor being going into overspeed condition, right? Okay, so the speed of the rotor is sensed, and there's a crowbar. The crowbar can be either active or passive, which basically shorts the rotor winding and basically dissipates all the energy through a discharge resistor. So that is how the rotor winding is protected, of the wind turbine is protected when there is a network fault. Also, to avoid overspeed, there's a speed protection for the rotor. Basically it senses overspeed and basically stops the rotor from. And also we have undervoltage and overvoltage protection requirement as well. Okay. For the challenges, like I made mention, I think I did mention in the earlier slides that as you have the deep penetration and basically eventually continuous penetration of these wind turbines and inverter-based resources to the network, definitely there's a lot of challenges, and one of the challenges has to do with basically protection schemes, and not having enough the inverter-based resources to not produce inertia to the grid or the AC power system network. As such, availability of short circuit that is required by these protective relays is reduced. So basically it becomes very challenging to detect these faults. Also, for grids that operate in island and connected mode, and during island mode, basically the fault current that are produced is about 2 to 3 times. And when it's connected in connected mode, basically, you have it connected to the transmission network, and the fault current basically changes, the contribution changes. So you're talking about 5 to about 14 times the fault current. As such, it requires an adaptive protection scheme that has to be designed to be able to detect fault operating conditions when it is connected in island mode, and also when it is connected to the transmission grid. Next is sub-synchronous resonance. If you have a wind farm that is connected to a transmission network that has a series capacitor, then basically, it is prone to sub-synchronous resonance, where the shaft of the turbine generator basically resonates with harmonic frequencies, and basically can result in the breaking of the shaft and the failure of this wind turbine. As such, system studies are performed, prior to the installation of these wind farms, especially when you have a prone series transmission line that has a series capacitor. Remember, some of these transmission lines, some of the utility companies and transmission companies install series capacitors just to be able to decrease the reactance and basically transmit higher power. And it becomes a challenge if you install a wind farm that is in close proximity to this series transmission lines. Next is fault write-through, which basically leads us to grid code requirements. Basically there are write-through requirements. That is temporary reduction of active power. That can be programmed. It's a software programming. That is when there's a fault, basically results in a temporary reduction of active power until the fault is cleared, and basically you can resume power production. Then you can also have a temporary reduction of active power and also a boost. That is, an increase in reactive power, to support when there's fault. Remember, the voltage goes down, and basically you need a reactive power to boost the voltage. Next, I think that is the last, wind turbine. That is type 4. Okay, so type 4 wind turbine can either be a one rotor or permanent synchronous generator, right? One rotor means that it has a gear system, and a brush system and a slip ring, And a permanent synchronous generator means that, it does not have a gear system, it does not have a slip rings, it does not have a brush system. It just has a permanent magnet, has a larger number of poles, which basically leads to slower speed. So the advantage is that, like I said, if you have a permanent synchronous generator, you can eliminate the gearbox and basically eliminate additional maintenance. But this utilizes an AC DC converters that are basically fully rated converters that are connected back to back. Compared to the Type 3, the Type 3 utilizes fractional rated converters, and that is 30%, which basically translates into lower cost and lower conduction and switching losses. But for the Type 4, it has fully rated converters, basically translates into higher losses. Okay, so the absence of slip rings and brush also introduces additional maintenance. I made mention about that, So basically, this becomes an ideal candidate, the best candidate to utilize this type of wind farm for offshore wind farm capability. This wind farm allows you to achieve the full speed, regulation. For the Type 3, it allows you to achieve plus or minus 30% speed regulation, but this allows you the full 100% full speed regulation. It allows, basically reactive power exchange, both active and reactive power exchange with a grid. Like I made mention, I think I did mention about the disadvantages. Basically, it results, because of the full-scale converters, it results in higher switching losses, and basically the initial capital cost can also be high because you are utilizing the full-scale converter, and also high harmonics. Okay, so remember I made mention that because of the permanent synchronous generators, you have let's say you can have a 84 pole wind turbine permanent synchronous generator, right? It can make basically the rotor very heavy, right? And also that adds to weight on the substation, offshore substation platform. So this one is just a schematic of how the Type 4 wind turbine looks like, So like I made mention that the gearbox can be optional. You can have it for the wound rotor induction type, or the permanent synchronous generator, or the squirrel cage induction generator type. These are all integrated to a full capacity power converter. Basically, you can have this installed in the back-to-back configuration. That is, it converts from AC to DC, DC to AC. So next is a scheme, of how the wind farm is integrated to the onshore, right? Okay, so you have the offshore wind farm, right? You have it over here, and they are connected in different arrangements, and the arrangement itself is a different studies that is performed, based on optimization and economics, and we have different radial star, different, and basically you have inter-array, the arrangement is called array, and you have inter-array cabling between these wind farms. Then basically you have AC cable from there to the collection point, offshore collection point, and basically the transformer that steps, it to an AC exporter transmission system. Then it goes to the offshore HVDC substation, and this is where the switch gear and also the converters are located. The offshore converter is located. Then from here is the DC side, so you have the DC transmission cable, positive, negative, and that goes to the onshore HVDC MMC converter. Then from here it is inverted back to the AC, and it goes to an interface power transformer that steps the voltage from a lower voltage to a higher voltage, because before it goes to the transmission towers, and it is transmitted to the load centers. So now let's talk about the topology, what I am presenting for this presentation, right? And what basically I modeled on. Okay, so the test topology, consists of 1.8 gigawatts offshore wind farm. Like I made mention in the previous slide, right? I presented to you quite a choice of permanent synchronous generator to be used for offshore wind farms, right? I made mention that the reason being that it doesn't have basically a gear system. It doesn't have a slip ring. It doesn't have brushes, right? So less maintenance. And also it is very tolerant to great disturbance, So, and basically, avoiding, failure due to, it having slip rings and brushes, and it having only permanent magnetic synchronous generator, it becomes the ultimate choice to utilize it for offshore wind farm. Okay, so now let's talk about, each aggregate of our wind farm. We have a wind farm each rated at 5 megawatts and 690 volts. And each wind farm has 180 units. Okay, so each wind farm has a rating of 900 megawatts. Right. Wind farm 1, 900 megawatts. Wind farm 2, 900 megawatts. And that is a permanent synchronous generator modeled in an aggregate model. And what does aggregate means? The aggregate means that I've put all the megawatts together for each wind turbine. Each wind turbine is rated at 5 megawatts times 180, that's 900 megawatts. So I'm modeling this one as a current injection source. That is the current injection, of each wind turbine times the number of units. So the output of this wind turbine, being 690 volts, is integrated to a step-up transformer. A step-up transformer basically steps the output voltage from 690 volts to 66 kV volts AC collection level, right? And the reason why 66 kV AC collection level is utilized is based on economics, and best choice. And most of the offshore wind farms that are currently in commercial operation are being installed. They are all shifting from 33 kV AC collection point to 66 kV AC collection point. Like I made mention that it has to do with a lesser array of cables, lesser losses, and also lesser maintenance because the number of cables are much smaller. Okay, so you have the cable from the output of the wind turbine to the AC collection point, 66 kV, being modeled in a nominal pi configuration because of the shorter length of cable. Then from the 66 kV AC bus to the step-up transformer that steps the voltage from 66 kV to 230 kV transmission level voltage. That cable is also modeled in nominal pi because of the shorter length of the cable. So these transformers basically they are all connected in parallel. Two of them for each wind farm. They step the voltage from 66 kV to 230 kV to achieve a 230 kV AC bus on the AC side of the offshore MMC, right? Each transformer is rated at 475 MVA, and the impedance is 10%. So the converter at the MMC side, at the offshore side, is a modular multi-level converter, and it's a half-bridge salt module, and it's rated at 2,000 megawatts, right? It was basically modeled in a detailed equivalent model. And what it does is basically, to convert the AC power to a DC power equivalent, right? Okay, so we have a DC transmission cable over here, and that is modeled in the frequency-dependent phase model, right? Just to capture, the frequency-dependent parameters, that is the inductance and capacitance. So the rating of this DC transmission cable is plus or minus 320 kV, and the transmission distance is 150 kV. So on this DC transmission cable, I am applying faults at various sections of the DC cable. Okay, so I'm applying faults at right at the terminal of the converter, which is going to be at the onshore converter, and that is going to be 0 kilometers from these converters. Then I'm applying fault at 20%, that is going to be 30 kilometers from this converter. Then I'm applying fault at 50%, so that is going to be 75 kilometers from this converter. Then I'm applying fault at 112 kilometers. Then right at the terminal of this offshore converter, that is 150 kilometers from this one. Okay, so then again, I'm applying basically I'm incorporating various fault resistances, and those fault resistances are 0 and 5 ohms, 20 ohms, 50 ohms, 75 ohms, 100 ohms, and matter of fact, I could add 200 ohms fault resistance to it. So this converter is basically the onshore converter, onshore converter, and that is also utilizing a half-bridge sub-module. And what it does, it inverts the DC power or DC voltage to AC equivalent, to achieve a 230 kV AC bus. So this is basically onshore AC substation. Basically, that's it. And this is basically your submarine cable. This basically the undersea cable, and this one is the substation platform where the converters are located, and this is where the collection point are located on a different power platform, and this is where the step-up power transformer is also located on an offshore platform. So from this AC bus, 230 kV AC bus, we have a cabling, and basically we have a nominal pi cable that is modeled to the step-up transformer that steps the voltage from 230 kV to 400 kV transmission level voltage. So we have a 3 parallel transmission transformers and transmission lines, and these on the high side, the 230 kV transmission, 400 kV transmission line are basically 2 circuits, that were modeled, and that integrates 3 parallel AC grids with a short circuit ratio of 3, X to R ratio of 20, and a frequency of 50 Hertz, and transmission voltage of 400 kilovolts. Okay, so as you can see over here, right, this is an aggregated model. So if this model has to be modeled in a detailed equivalent, this is how it's going to look like. So this one is more of a radial connection. Remember, I told you that the wind farms are arranged in different arrays, and different configurations. We have radial and radial star. Radial star is the most common. And if you want to introduce redundancy, you can have a ring in it. Okay. Okay. So now let's pivot to what a hybrid DC circuit breaker is and how it interrupts a high voltage DC current. Remember, I made mention that if you utilize a half-bridge sub-module converter, definitely, because it lacks the fault blocking capability, and it lacks the ability to be able to control a DC fault, you require basically, an HVDC breaker to provide the intervention and basically interrupt the fault as fast as quickly within 2 to 3 milliseconds. So now let's talk about the types of HVDC circuit breakers we have. We have the mechanical resonance. So basically what it does is it's utilizing a resonance circuit to achieve the artificial zero crossing. Remember, I made mention that because DC faults lack zero crossing, you have to, compared to the HVAC counterparts, you have to basically create an artificial zero crossing for it before you can be able to interrupt the fault. Then you have a solid state DC breaker. Basically, what it does is, it utilizes IGBTs or GTOs, gate thyristors, thyristors. Then you have the hybrid DC circuit breaker, and I'll show you, what the hybrid DC circuit breaker, how it looks, Okay, so for the fault interruption scheme, the goal of any DC circuit breaker is basically, to interrupt the fault and commutate the fault and absorb the energy, because as it is interrupting the fault, basically you are basically, it's a lot of energy from the L and C part of the transmission network, that basically you need to commutate and have an absorption scheme. And I'll show you what consists of the commutation branch, the interruption branch, and the absorption branch. So for the process to achieve the artificial zero crossing, you need a counter voltage. So basically, what these DC circuit breakers do is basically generate a counter voltage, and basically based on that create a zero current in the main path and be able to absorb all the energy and interrupt the high fault. Okay, so next is a picture of how a DC circuit breaker looks. On the left side, it's basically resonant type of DC circuit breaker, and basically the mechanical DC circuit breaker, and on the right hand side is the hybrid DC circuit breaker. So basically, the ones on the right side are basically the technology of choice these days. If cost is not a factor, if cost is a factor, then basically the one on the left side is basically the technology of choice. So now let's talk about how the current interruption basically occurs, right? Okay, so you have basically operating DC voltage, right? And you have a current, right? Okay, so all of a sudden there's a fault, right? And because I told you that, remember I made mention that because of the very low resistance of HVDC circuits in the DC cable, right? Because the frequency is 0, there's no reactance, and there's nothing to impede the fault. Okay, so there's a steep rise in current. So as it gets to this part, then that is when the counter voltage basically comes into play. So basically the circuit breaker creates this counter voltage, and basically that helps basically to push the current to a zero crossing and where it is interrupted, right? So the goal is basically to interrupt, and that is the main branch and the auxiliary branch, and this is the main branch, and the metal oxide varistors to absorb the energy. Okay, so now let's talk about the fault characteristics of the half bridge. Remember, I made mention that the half bridge submodule is what I selected for this presentation, right? And let's talk about the DC fault characteristics. Okay, so I think I did discuss with you the operating states of the half bridge submodule, right? So the very top here it's the upper arm, and the very bottom here is the lower arm. And like I told you that each one consists of a series of this. It could be hundreds, 200s, 300s, 400s, all the way up to thousands, all connected in series, cascaded together to achieve the required voltage that you want, right? Okay, so on the right hand side are the operating state, and like I made mention that these are the operating states. The main states are operating states are 4, right? Okay, so you can have the charging states. So the charging state, what does it mean? Charging state means that at the top IGBT is being, there's current path that is flowing through the diode, through the submodule capacitor to charge the submodule, right? So it's flowing right here through this freewheeling diode through the submodule capacitor to fully charge the submodule, right? So that's it, that is charging. Then the next one is the bypass state, right? So this is the bypass state where I'm bypassing the submodule. So basically, what am I doing? I'm flowing through this IGBT right here, bypassing it. Right? And the next state is discharge. And this discharge state basically occurs during faults, right? So when they say DC faults, and basically that's when there's a full discharge of this submodule, the charge, right? The charge is the capacitance that is in it. So it is basically, discharging through this circuit right here. And the next operating state is another bypass state, where basically, I'm freewheeling through the freewheeling diode, right? So now let's talk about the DC fault characteristic of the half-bridge sub-module for a pole to ground fault and a pole to pole fault. Remember the symmetric monopole configuration, we have a positive pole and a negative pole, right? Okay, so we can have a pole to ground fault and we can also have a pole to pole fault. So for a pole to ground fault, we have two stages. When there's a pole to ground fault, basically there's a slight drop in the voltage of this submodule, fully charged submodule capacitors, So basically it doesn't lead to a complete discharge of this submodule. Yeah. Next is the cable discharge, So the cable discharge is basically considered as stage 1, where the DC cable fully discharges. Yeah. And through the freewheeling diode. So that is when the bypass comes into play, where the DC cable, the charged capacitance basically fully discharges through the freewheeling diode through the bypass mode. Then the next stage is stage 2. It's a grid side current feeding stage. That is when the grid side also feeds the faulted point. So it feeds the faulted point through the freewheeling diode until it basically reaches steady state operating condition. Right. Next is pole to pole fault characteristics. Right. Okay. For pole to pole, on the other hand, we have 3 stages compared to pole to ground. So for pole to pole fault, you have a complete pole to pole short. Right, so voltage basically goes to 0. So the submodule voltage basically goes to 0, which requires a full discharge of the capacitor of the submodule. So that is considered stage 1, full discharge capacitor. Then the next is the cable discharge. So that is when the cable, the charge capacitance of the cable basically comes into play, based on the fault. So the DC cable basically fully discharges through the freewheeling diode to the faulted point. And the next stage is stage 3. That is when the grid side basically also feeds the fault after the cable discharge is completed. Now let's talk about the parameters of the MMC modular multi-level converters for both the onshore and offshore converters that I selected. It's a 77 level converters, So basically, I have 77 of these half-bridge submodules. So the rated power of is 2,000 megawatts. The AC side voltage of both MMCs, onshore and offshore, is 230 kV. The nominal frequency is 50 hertz, and the converter transformer, this is the rating. We have 230 kV to 370 kV. Remember, the converter on the offshore side, right? Okay, so I have a AC bus, of 230 kV. I've been able to step it up through transmission level exporter transformer, and that steps the voltage from 230 kV to 370 kV. The goal is to basically achieve a 370 kV AC voltage level, which will produce a equivalent DC voltage that I need. I need a plus or minus 320 kV voltage. That is pole to ground voltage of a 320 kV and a pole to pole voltage of 640 kV. So I should be able to step up the voltage to the required AC voltage, which will allow me to get the DC voltage that I need. Likewise, on the onshore MMC, same thing. I should be able to step it down to the required transmission level voltage before the step-up transformer that steps it up from 230 kV to 400 kV. Okay, so the nominal DC current is 3.12 kV. And for the DC voltage, I have a plus or minus 320 kV and a pole-to-pole voltage of 640 kV. Then for the number of sub-modules, right, I have 76. I have 38 in the upper arm, and the lower arm I have 38. So the total number of level is 76 plus 1, which gives me 77. Then the rest is just the other parameters, the capacitance, then the sub-module, inductance, and IGBT states. When it's on, this is the resistance. As you can see, when the IGBT is on, it has a very low resistance, and when it is off, it has a very high resistance. Now let's talk about the switching frequency. Remember, I made mention, this is what basically distinguishes the modular multi-level converter from the traditional level, 2-level, 3-level voltage source converters. The traditional 2-level, 3-level voltage source converters utilizes a switching frequency of 1 to 2 kilohertz, whilst the MMC utilizes 150 hertz. So basically, this results in a lower conduction and power losses. The DC transmission cable that I'm utilizing is 150 kilometers. Okay, so now let's talk about the structured control for the MMC that I'm utilizing. In the previous slides, I made mention of just general control for an MMC, but this one is just the structured control that I'm utilizing for this presentation, right? Cool. So for an MMC, it has two control levels: the upper and the outer level control, and the inner level control, or the lower level control. Okay, so I have dispatch set points, right? I have DC voltage and active power, which basically comes from the dispatch center that is sent to my outer or upper level controller, right? Okay, so I have onshore MMC, which is basically operating in a grid following. Basically, what it does is it mimics what the grid does through current injection, right? So the grid side MMC is operating in a DC voltage and an AC voltage control, right? Okay, so through decoupled current controller, that is ID, IQ in the lower level. So I'm controlling the ID voltage to control my DC voltage. I'm controlling my IQ current to control my AC voltage. On the other hand, my offshore MMC, I'm controlling it in an island control. And island control, it's basically grid forming. And actually, that is a game changer for this offshore wind farms, through grid forming, control. And what it does is basically it's able to build its own voltage and frequency, just like the AC system, right, through a phase lock loop that is integrated to the AC grid. So for the lower level controls, right, remember, for the onshore MMC, I'm controlling the DC voltage and an AC voltage, right? So I should be able to control my direct axis current and my quadrature axis. My direct axis current, I'm controlling it to be able to control my DC voltage, and I'm controlling my quadrature axis current to be able to control my reactive power and control my AC voltage. In addition to that, we have capacitor voltage and balancing scheme, because for the half-bridge sub-module, right, you have basically, capacitors, right, and you need to balance all the voltage. So you need algorithms that is going to basically make sure that all the sub-module capacitors have the same voltage threshold. Then also there's something they call circulating current suppression, right, algorithm, right? Okay. On the AC side of the MMC, right, you will see that basically you have the upper arm, the lower arm, in between each phase, right? There's going to be different voltages, right? Basically, this will result in circulating currents. And so basically, you need an algorithm that will basically suppress this circulating currents to minimum level. And this is integrated to a pulse with modulation, basically, that provides the firing signal to the MMC valve groups to the converter. Now, let's talk about the fault clearing strategies that are out there, right? Okay, so basically, this is all based on academia, and hopefully, I'll say that the only fault clearing strategy that is in existing in commercial operation is the non-fault, non-selective clearing strategy utilizing AC circuit breakers, So Basically, this is all based on our industry research, and we have the fully selective fault clearing strategy. Then we have the partial selective fault clearing strategy. Then we have the non-selective fault clearing strategy. And this is all based on a promotion research, and based on work package 4 and 5, and this is what they came up with. Okay, so their work package basically, clarifies and basically, delineates fault clearing strategy into 3 areas, and that is fully selective, partial selective, non-selective. Then Senelec, on the other hand, delineates their strategy. The fault is based on the impact. That is when there's a network fault. Their fault strategy is based on how the impact the network fault will have on the wind farm. And that is based on the amount of active and reactive power that is basically sensed at the point of interconnection. SIGRE, on the other hand, also classifies, fault clearing strategies into 3 clearing strategies, and that's fully selective, partial selective, and non-selective fault clearing strategy. Okay, so now I made mention of a fully selective fault clearing strategies, and that is what I'm utilizing for this. So for the fully selective fault clearing strategies, what I'm utilizing is for this model, I'm putting the hybrid circuit breaker here, hybrid DC circuit breaker, and at each ends of this DC transmission system. So one here and one here. So the goal is for a fully selective fault clearing strategy is to be able to, when there's a fault here, right, to be able to detect and isolate the fault, whilst it allows the healthy sections of the multi-terminal DC grid to continue in operation. So this one is a typical example of a meshed grid, a meshed multi-terminal DC grid. So as you can see, we cannot, if we were to have a non-selective fault clearing strategy utilizing AC breakers, right? What is going to happen if there's a fault, right? It's a DC side fault, and we trip all these AC side breakers. Basically, it's going to lead to a total collapse of the whole multi-terminal DC grid, and we don't want that, right? The goal is to basically detect and isolate the faulty section and allow the healthy sections to continue in operation. Okay, so the hybrid DC circuit breaker, this is an example of the hybrid DC circuit breaker, how it looks like. Okay, so let's talk about the architectural components of the fully selective fault clearing strategy. It basically consists of hybrid DC circuit breaker at each end of the DC transmission system, and that is what I showed to you, right? This two. And if for MTDC, then it's all these circuit breakers on each end. Then the half-bridge sub-module MMC converter. So this MMC converter utilizing a half-bridge sub-module. For the non-selective fault clearing strategy, right? I'm utilizing it as a backup protection, for this. So, utilizing a selective as a fault clearing strategy as the main fault clearing strategy, I need a backup. Let's say if if the breaker, DC circuit breaker fails, and I will need a backup, So the backup I'm utilizing the AC side circuit breakers, to interrupt the fault, after a time delay. On the other hand, you can also utilize, if you have a fault blocking scheme, right? If you have a converter that utilizes a fault blocking scheme, then basically, or a hybrid fault blocking scheme, you can utilize that one as well. Okay, so for the non-selective fault clearing strategy, like I made mention, is considering the whole grid as one protection zone. So basically, there's no selectivity in it, So once this breaker, AC side breaker trips, basically the whole MTDC grid is basically down. Next is partial selective fault clearing strategy. As you know, from symmetrical monopole configuration, point-to-point. As it evolves to multi-terminal DC configuration, that is 3 terminals, 4 terminals, 5 terminals, and eventually, about 6 terminals, and eventually to DC grids, right? There is the need to incorporate partial selective fault clearing strategy, and as we have DC to DC converters, that is going to be integrated into this. It is very important. That is when a partial selective fault clearing strategy comes into play. Yeah. There isn't quite, when you have a fully selective fault clearing, it is not, ideal to introduce a partial selective because it's very, expensive, high cost, and it's, because you are utilizing a DC to DC converters, and that's very expensive. Yeah. So hopefully, in the future, as technology becomes cheaper, basically the cost will go down. Yeah. And also, when, non-selective fault clearing strategy, it's not an option, so that is when, you basically utilize a partial selective fault clearing strategy. So what it does is it splits the DC grid into zones after the fault. So you have a faulted zone and a non-faulted zone, and basically you de-energize the faulted zone, and basically, after de-energizing by tripping the DC circuit breakers in the faulted zone, and basically you allow the healthy section in the non-faulted zone to resume. Yeah, like I made mention that this type of clearing strategy is expensive, because you have to be utilizing fault blocking converters, and that is the fault bridge sub module, which is very expensive. Remember I made mention that requires a higher number of semiconductors, IGBTs, so about 4 of them for each sub module, and also it requires DC to DC converters, which can be very, very expensive. Okay, so now let's talk about traveling wave. Yeah, so traveling wave, when there's a fault on a DC transmission cable, right? What happens? It results in basically currents and voltages, and this currents and voltages the faulted point generates into current traveling wave and a voltage traveling wave. So at the faulted point, these traveling waves is generated, and basically it moves to each other end of the converter. So the converter basically acts as an impedance for this traveling wave, where basically it gets reflected, refracted, and basically it's then back to the faulted point. So it basically goes back and forth until it is attenuated. So basically we have the voltage traveling wave and the current traveling wave from each side. From the left, voltage traveling wave from the left side, voltage traveling wave from the right side, current traveling wave from the side, left side, and current traveling wave from the right side, and propagation constant, gamma, and the velocity of the traveling wave. That is the telegraph equation. Okay, so now let's talk about the proposed protection scheme. Like I made mention that to utilize this protection scheme, that is fault detection, fault processing schemes on its own individually, there's a drawback, and I made mention of it in the earlier part of the slides, right? So there's the need to implement a hybrid protection scheme, which will basically leverage the advantages of each, and basically minimize the disadvantages of each protection and detection processing scheme, right? Okay, so for this, I'm basically utilizing the traveling wave based method, and this is based on the behaviors of the traveling wave during propagation, and basically there's a difference between when an internal fault occurs and an external fault occurs. The traveling wave basically behave differently. The polarity is different. Polarity is different from current. Polarity is different from voltage for internal and external, right? Okay, so in addition to the traveling wave based method, I'm adding a time frequency domain, and basically in addition to that, utilizing discrete wavelet transformation and multi-resolution analysis based method of processing. So this is the hybrid protection scheme, and basically that is basically the future of high voltage DC protection relays, right, to utilize a hybrid protection scheme. That is a protection scheme that consists of a traveling wave and discrete wavelet transform in a multi-resolution analysis, or continuous wavelet transform in a multi-resolution analysis, or a combination of a traveling wave and artificial neural networks and machine learning techniques. So the discrete wavelet transform will be calculating the high frequency components of the DC fault. Basically spit out the wavelet coefficients and calculate the arrival time of the traveling wave. And basically, the multi-resolution analysis allows basically decomposition at different frequency ranges, and also detect the traveling wave at when these different frequency ranges have been decomposed. Then, again, the entropy of the detailed coefficients, right? Remember, I'm utilizing a discrete wavelet transform and multi-resolution analysis to basically perform calculation of detailed coefficients, and based on the detailed coefficients, I'll calculate the entropy energy, and basically that will be the basis of detection of faults. Okay, so for the discrete wavelet-based protection, transform-based protection, I'm utilizing the wavelet coefficient, right, and basically for the fault detection, and basically protection criterion, and that basically detects the wavefront of the initial traveling wave. And I'm also utilizing the wavelet entropy to basically identify initiation of fault detection. To distinguish between internal and external fault, remember I told you that traveling wave, behaves differently for internal and external faults. They have different polarities for current and wave voltage, and also the detailed wavelet coefficients and relative entropy. These are what I will utilize to basically distinguish between an internal and an external fault. Now, for the fault classification, I should be able to classify a fault, and distinguish between a fault and a steady state operation. And also, after fault classification, I should be able to identify which type of fault. That is a pole to ground fault and a pole to pole fault, utilizing machine learning algorithm, that is support vector machines. Okay, so now let's talk about the process of how the DC fault will be processed. Okay, so I'll basically capture voltage and current signals from a PS card simulation of various fault scenarios, and that is on the DC side, on the AC side, and basically export it to MATLAB for processing. Then basically I will utilize feature extraction. I need to basically utilize different drawbacks, different Mother wavelets, and that is drawbacks, simulate and correlate Mother wavelet to perform the feature extraction. And based on that, I'll select the right Mother wavelet based on the best similarity with the fault current, and also the optimum decomposition level. Then also variation of the sampling frequency. Remember, I made mention that we vary the sampling frequency, to capture, the effect of cost reduction, and basically the protective relay, the data algorithms, and basically processing times, computational burden being lower. Then basically determine the magnitudes of the detailed coefficients, and basically set up the thresholds, and basically utilize support vector machines to determine the arrival time. Then basically set the threshold based on adding basically reliability coefficients, and based on margin 5 to 50% in addition to that. So next is a flowchart, basically that talks about the DC fault processing scheme, right? Okay, so if you have a signal with let's say 100 kilohertz sampling frequency, remember I utilize 20 kilohertz all the way to 100 kilohertz. So basically if it is 20 kilohertz, basically the Nyquist centered frequency will be different, So 20 kilohertz Nyquist centered frequency will be 10 kilohertz. But let's consider 100 kilohertz, where the Nyquist centered frequency is 50 kilohertz, right? So basically, I have a Willet function, and I have pass filter it and downsample it by 2, right? And basically from that I derive the high frequency detailed coefficient, and from there I have it as an output. From there I determine the wavelet entropy, right? Okay. On the other hand, the scaling function, that is the low pass filter, and downsample it by 2, and that is the low frequency detailed coefficient. And basically, then this becomes the input for the next stage. Then it continues like that. So now let's talk about the MATLAB code to process the fault signal. I wrote a MATLAB code and basically, to process the fault signal, and this is what the code explaining what the code, the processing, the getting feature side of the code, what it looks like. So X is basically what the signal is. It could be a DC fault signal, AC fault signals, and basically those are rows and columns, and the window size I selected is 32 samples, and increment is 16 samples. So the window size 32 samples is good enough to cover, where the fault occurs, And of course, sampling frequency, I've varied it between 20 kilohertz and 100 kilohertz. So, like I made mention that we have 100. Let's take an example. We have 100 kilohertz, sampling frequency. So the Nyquist criteria is 50 kilohertz, right? Okay. So the first level of decomposition, this is what I'll have, and the second level, the third level, the fourth level, the fifth level, and the sixth level. Okay, so now let's talk about the flowchart for the proposed protection criteria. When protection will start, right? Okay, so I have, my protection starts, my measuring basically starts, right? Okay, so I'm measuring current and voltage, and basically, utilizing current measuring schemes. Let's say, utilizing Rogowski coil, or you basically, CTs, and basically, fiber optic sensing CTs, and other voltage sensing CTs, VVTs. Then basically I export this data into MATLAB for digital signal processing. Then basically I perform decomposition and extraction processing of the signal, and basically I determine the wavelet, high frequency wavelet coefficients as an output. Then from there I determine the entropy also as an output. Then based on that, based on our optimization level, I will determine the threshold when protection starts based on the entropy energy. If the entropy energy is greater than the threshold, then protection starts. So that's a rule-based fault detection. If it is below, then it goes back, and basically the flowchart basically repeats itself. So next is the protection window for fault detection. So before protection starts, I have a delay of about 0.2 milliseconds, Then the window for protection criterion is about 2 milliseconds, And a sliding window is about 32 samples. Okay, so the reliability factors is based to account for uncertainties, that is noise, disturbance, and lightning and switching disturbance. And this actually applies to the AC side. Right? Okay, so to distinguish between an internal and external fault, so remember I indicated that we can utilize the polarity and the directional features of voltage and current. Okay, so for internal fault, the current traveling wave that is detected at the local and remote have the same polarity, but the voltage traveling wave have opposite. So we can utilize that to basically identify an internal fault, and also for an external fault is the opposite. The first current traveling wave that is detected at the local and the remote have opposite polarity, but the voltages are the same. Okay, so now let's talk about distinguishing between internal and external fault. Okay, so as protection continuing from slide 69 and providing the supervisory, role, and as a continuation of this slides. So what we do is basically, determine the high frequency wavelength coefficients of the DC faults and AC faults, then determine the entropy energy. Then from there, compare it with the polarity. Then basically we can determine if an external fault has occurred or internal fault has occurred. And if an external fault has occurred, the DC protection blocks and allows the AC protection to take care of it. Then if an internal fault is declared, then basically we need to determine the fault distance and classification of fault. So that itself takes us to the next slide, and where basically providing a supervisory from the other slide, basically we determine the arrival times of the traveling wave. And the arrival times of the traveling wave can be determined from support vector machines during processing. Then from there, I know the velocity, I can calculate the velocity. I know C, which is speed of light, and I know the L, that is cable inductance. C is the capacitance of the cable. Then I can determine the velocity and basically determine the distance where the fault occurred. Then from there, basically, I can compare the actual faulted distance and calculated fault distance, and basically determine the error, percentage error. So now let's talk about the classification. So same thing, providing a supervisory protection scheme from the earlier slide where protection starts, right? Okay, so once I've determined that I have an internal fault, then basically I need to determine what type of fault classification it is. Whether it's a pole to ground fault or pole to pole, and I'm utilizing a machine support vector machine for that, machine learning for that. So next is a flowchart of how the support vector machine will perform the classification for pole to ground fault and pole to pole fault. Okay. So next is polarity. The polarities I'll utilize for measuring instruments. Okay. So for steady states, right? If you have a model, this model was done in PS card, right? So the goal is basically to prove that the model it performs as it's supposed to, right? So I perform a steady state simulation, right? And basically, I was able to achieve, the required peak phase to ground voltage, and that is instantaneous voltage, and that is what is required. Then on the RMS voltage, I was able to achieve 230 kV line to line at 0.09 seconds, and for the offshore frequency, that is island control, and grid forming control, I was able to achieve that frequency, 50 Hz frequency within this time. Then also, for the current, right, peak phase to ground, instantaneous, I was able to achieve it, what is required. Then for the active power, for onshore MMC1, I was able to achieve 1698 megawatts at 10 seconds. Next is measurements on MMC2 side. So similarly, I was able to achieve the required, instantaneous AC current, peak phase to ground current at 9.74 seconds. Then active power, 1784 megawatts at almost quite close to 10 seconds. Then peak phase to ground voltage, I was able to achieve it. Then VRMS line to line voltage, I was able to achieve it within 1.5 seconds. Now let's talk about the DC link, DC current flow, and DC voltage to ground, and DC pole to pole voltage, right? So for the DC current, right, 2.5 kiloamps, was able to achieve it within 9.09 seconds. Okay, so this is the steady state, operation DC current that flows, right? For from MMC2 to MMC1, from MMC1 to MMC2. Okay, so for the DC voltage to ground, pole to ground voltage, I was able to achieve it 320 kV to ground minus 320 kV to DC. Then pole to pole, 640 kV DC voltage, I was able to achieve that. Okay, so this is basically, a table that shows, steady state results of steady state simulation. And like I indicated, energization of the converters, right? Okay, so MMC1 converter is operating it's located onshore, right? And it's operating in DC voltage control and AC control. And remember, these are the outer or upper layer, controls, right? And it's integrated to lower level inner controls. That is the current control, direct access control, quadrature access control, right? So based on the set level of ID, IQ, based on the DC voltage and the active power that is sent by discharge, right? The ID and the IQ is controlled to achieve the reactor. IQ is controlled to achieve, vary the reactive power to be able to control the AC voltage, and similarly, ID is controlled to control the active power to maintain the DC voltage, right? So during energization, we energize the DC link, right? Okay, so energize the DC link to the required DC voltage, right? And this is a pre-charge through DC insertion resistance, right? Okay, so that is how the DC link is charged. Then, after the DC link attains its full voltage, MMC1 is basically deblocked, for it to start operation. Then after that, we regulate the DC voltage of the DC link. Okay. On the other side, MMC2, the converter that is located offshore, right? Its control mode is island, and basically its control mode is to build the required voltage, AC voltage and frequency, just like the AC creator utilizing a phase lock loop controller. So after DC voltage regulation, after we have performed the DC voltage regulation to the right DC voltage levels, then that is when the DC blocking occurs for the deblocking occurs for the MMC2 offshore converter. Then after that, basically this occurs after 0.6 seconds. Then the AC breaker is closed to regulate the AC bus. Then after that, deblocking of the wind cluster 1 and 2. Similarly, the next slide shows nice tabulated results of when you have half a load. Then basically simulation charts. Basically, that's a PS card simulation charts that shows basically all that is required to be measured for the DC side, DC link, or all the parameters, the converter parameters, and the AC side parameters for half load. Next is simulation results for two-third load, right? And this is all put in a nice table format. Then next is PS card simulation, that shows nice charts of what is required, all the parameters that are supposed to be measured on the DC link, and for the converter, active and reactive power, and also the AC side, voltages and currents, instantaneous currents and voltages. Now let's talk about AC side fault simulation for MMC1, MMC2, right? Okay, so I applied a three-phase to ground fault with 0 ohms. Okay, so on the AC side, similarly, the faults were varied. We have 5 ohms, 20 ohms, 50 ohms, 80 ohms, 100 ohms, and basically the three-phase to ground fault was applied. And basically, as you can see over here, this basically simulation that shows how active power, basically, how it went down, then basically it recovers. As you can see, the offshore small slight perturbation in basically the offshore frequency. So that should tell you the deblocking action of basically the converters. So basically, what all the faults that occurred on the AC side never got transmitted fully to the other side of the converters, right? Okay, so next is basically the recovery voltage for the RMS voltage as well, and the RMS current. So next is basically for MMC2, and as you can see, these are the simulation. The last slide is basically the charts. That is what is seen on the MMC2, but MMC1, this is what is also seen over there. Next is a single line to ground fault, right? Okay, on MMC. So similarly, same thing. That shows all the simulation charts that for active power and how the active power dipped and recovered, and basically how RMS current also dipped and recovered, and basically instantaneous current also peaked and recovered, and RMS voltage also dipped and recovered. Next is basically on the MMC2 side, right? What happened, and as you can see, nothing affected, on the MMC2 side when there was a fault on MMC1. So that itself tells you that the DC converters, the converters are acting as a firewall and deblocking, preventing the transfer of faults on the AC side propagating to the other side. As you can see over here, the DC fault current is 0. Okay, so now let's talk about faults on MMC2 side, right? Okay, as you can see over here, similarly, right? Okay, so a three-phase to ground fault, it dips and basically it recovers for active power and instantaneous current. But similarly, it dips and recovers, and RMS voltage, same thing, recovers, and RMS current, same thing, it dips and recovers. Then that for the MMC link, these are all the parameters that were, basically, it results in a slight perturbation, and dip, and basically it recovers. Then basically measurement on fault. This fault was applied on MMC2, but we are basically measuring all the charts on the MMC1 side. So that shows you all the charts, Yeah. Next is single line to ground fault, and basically that shows you all the charts and all the measuring parameters. Okay, so this is a table of all the AC side faults, what was performed, as you compare it with a steady state. So you can see that actually there was a fault, right? As you can see over here, the fault and also the fault decreases with increasing fault resistance, as you can see over here. And as you can see over here, the DC voltage, also is the DC current is 0. And as you can see over here, when the fault occurs on the AC side, it also slightly, affected, the AC side voltage, as you can see over here, and a perturbation in the DC side voltage, all of them until it recovers. Similarly, for single line to ground fault, same thing, as you can see over here, it's basically results in, as the fault resistance increases, basically there is a reduction in fault currents. Okay, so why do we need DC breakers to meet the goal of multi-terminal DC and DC grid, right? As you can see over here, right? Okay, so these are measurements for the grid forming control bars. As you can see over here, when a fault occurred at time 20 seconds, right? So there was a big peak in peak line to ground voltage, right? Then it recovers. Similarly, on 60 kV bus 1, 60 kV bus 2. So these are basically the AC collection bars for the offshore wind farms, right? And similarly for the current, right? As you can see over here, there was a dip and it recovers, and similarly for the offshore frequency, same thing. There was some perturbation and it recovers. Then on the 230 kV AC bars, similarly, there was a peak, a rise in voltage, peak line to ground, then it recovers. And on the RMS voltage, same thing. There was a peak and it recovers. And same thing, as you can see, there was a power recovery, power dipped and recovered. Then on an MMC DC link, right, as you can see over here, was a big dip in active power and it recovers, right? Big dip in active power and it recovers, right? But the goal is, what we need to look at is the time for the recovery of the voltage. So that is basically why we need a hybrid DC circuit breakers. So we look at the time that the AC side circuit breaker was able to recover, basically the fault. That was about about 40 milliseconds, and that is a lot for this MMC converters, and that's not ideal for the power electronics. And that itself can cause a lot of chaos and basically collapse of the HVDC grid. So it requires an intervention, and the intervention means that we need a DC circuit breaker, hybrid circuit breaker, to basically implement the required selective fault clearing strategy. Okay, so similarly, faults were applied on the DC side, right? Okay, so for the DC side, for a pole to ground fault at 0 kilometers, that is very close to MMC1, right? With varying, fault resistance. These are all the DC fault currents, and basically voltages on the AC side, basically, the currents on the AC side. And pole to ground fault at 30 kilometers, that's 20% down the line. Then pole to ground fault at 75 kilometers, and pole to ground fault at 112.5 kilometers. These are all basically all the data that were acquired, and basically, that shows you decreasing fault resistance with fault currents, with increasing fault resistance and distance. Then this shows a pole to ground fault at 150 kilometers, and that is basically quite close to MMC1. Okay, so next is simulation charts that shows pole to pole fault at 0 kilometers. That is from terminal 1 onshore MMC1, right? So that tells you, fault occurs at 20, and basically slight dip, and basically this itself tells you, the need for DC circuit breaker, so that the fault can be cleared and basically recover. So this basically shows you all the charts: active power, instantaneous current, peak phase to ground current, and also RMS voltage, RMS current, active power for converter number 2 for pole to pole fault, and DC link parameters. And also it shows you the DC fault current right here. As you can see, 69 kA fault. That's a lot for at 20 kilometers. So that should tell you. And the rest is DC link parameters, DC pole to pole voltage, pole to ground voltage. Okay, so next is basically similarly, like I made, I showed you, for a pole to ground fault for various varying resistances and distances. Same thing. This one is for pole to pole fault, and all the way up to 150 kilometers, right? Okay, so now let's talk about the processing, right? Okay, so basically the goal is utilizing district wavelet transform, and basically you have a signal, right? So basically you have a sliding window, and you have an increment, and basically you are increasing the sliding window until you capture the fault, what you need. Okay, so basically, utilizing a multi-signal wavelet decomposition. So I'm utilizing an 8-step decomposition level. I selected 8-step decomposition, just to basically considering, computation burden. You don't want to have a lot of decomposition steps, because the higher decomposition steps that you have, it basically translates into higher computational burden, and also basically much longer time, basically, to detect the fault, and also it translates into cost as well, and basically, our goal is basically to cut down the cost of, the future DC protection, HVDC protection relays. Okay, so basically, I have each step, and basically, I'm basically decomposing it into approximate and detailed coefficients, high frequency and low frequency. So the window size is 32, and that is adequate to cover the fault signal, and window increment. Okay, so I'll be increasing it 16 until I cover the fault, and I'll be sampling frequency of 20 kilohertz, and the different mother wavelets that I'll utilize are these. So this is a MATLAB script basically that I used for data processing, and for calculating the detailed coefficients. So basically, detailed coefficients. So basically, these are all the detailed coefficients, and basically I I made a comparison, a table, tabular comparison of dowages and selectivity, right? And basically for various faults, pole to ground, various fault resistance and arcing resistance, and basically next is for various distances. As you can see over here, what we have is 75 kilometers, and next is 112.5 kilometers. All the detailed wavelet coefficients is all tabulated here. Then 150 kilometers, all the detailed. So basically, from there, I'll determine the maximum and the minimum, and from there, I'll add a reliability factor. So by basically, and that will be an indication, based on the maximum and the minimum. I'll be able to determine when protection starts. After adding the reliability factor. I'm looking at a reliability factor about 5 to 15%. Okay. So this also shows detailed wavelet coefficient for faults on the AC side, and, MMC1, MMC2. Okay. So feature extraction, very important. That the selection of the mother wavelet should be able to extract the features that matches exactly steady state AC and AC faults, DC faults. So I think Dalbridges and Simlet did a very well. Coil flex, there was a limitation. It couldn't go. It went only to coil flex 2 and coil flex 4. It couldn't go all the way to 8. And HAR, like I said, it's only 1. That also did well. So this basically shows you an excellent feature extraction that basically matches the steady state representation of steady state load. Okay, so next is feature extraction for faults, right? Okay, so as you can see over here, this is my PS card simulation of the fault signal, right? For DC fault, right? Okay, so in my MATLAB district wavelet transform code should be able to extract, exactly this fault signal, and basically, Dalbridges and Simlet did an excellent job, and basically even when I varied the sampling frequency all the way to 20 kilohertz, it was able to, basically extract correctly what the fault signal is. So similarly, for pole to ground fault at 30 kilometers, similarly, that is the original PS card DC fault signal that was created, that was generated, and this is the extraction from MATLAB. So as you can see over here, exact replica match. Then next is pole to ground fault with 30 kilometers at 5 ohms fault resistance. Similarly, same thing. As you can see over here, this is the original DC fault signal from PS card, and this is the extraction from MATLAB discrete wavelet transform using Dalbridges. So next is pole to ground fault at 75 kilometers. Pole to ground fault at 75 kilometers at 20 ohms. Pole to ground fault 75 kilometers at 50 ohms. As you can see over here, yes, actually, yeah, exact. Then pole to ground fault at 112.5 kilometers, 0 ohms. Yes, as you can see over here, if you compare this one to it, exact replica. So same thing, and as you go to pole to ground fault at 150 kilometers, same thing, exact extraction, Then next is pole to pole. This one is extraction of at MMC, on the AC side. So now let's talk about lightning disturbance and lightning fault representation. Like I made mention that the MMC1 that is located onshore is prone to lightning disturbance, and basically, so we need to consider that as a part of the protection scheme. So as you know, referencing this literature, basically lightning disturbance, even if it does not cause a fault, always has a high frequency component. and also has a low frequency component. Okay, so we can utilize that feature, So the high frequency component are also more, and the low frequency component are much lower, So when the lightning fault occurs, it basically, results in many of the low frequency components. So we can utilize these features basically, and generate basically some formulas to basically identify and be able to detect and identify and distinguish between lightning disturbance and actual fault. Okay, so next is a flow chart that shows lightning disturbance and lightning fault. Okay, so this is a MATLAB script code basically that shows adding Gaussian noise, to let's say, if you have a substation on basically you have a background operating noise at the substation at the industrial facility that is close to it, and so I added a 5 dB, 10 dB, 15 dB, 20 dB, 30 dB, 40 dB, 50 dB, 60 dB to the fault signal, and basically noised it and denoised it. So that is another code denoising it. Yeah. So this shows the signal being denoised, being noised. For single line to ground fault, it shows the signal being noised with the Gaussian noise. Then three-phase, fault, after noising it, I need to denoise it. Right? So the single line to ground fault, I denoised it. Then steady state, like I said, you can have a steady state operation without any fault, right? And the outdoor AI substation can be prone to, substation noise, and also noise coming from industrial facilities that are closer by, So that itself could corrupt these steady state signals that are being measured when the outdoor substation is in operation. Yeah. So this features shows denoising and basically extraction of and performing detailed wavelet coefficient after that. So this also shows feature extraction for different pole-to-pole fault. Right? Pole-to-pole fault. Pole-to-pole fault at 30 kilometers at 0 ohms. 75 kilometers for pole-to-pole fault at 0 ohms. Then feature extraction. Yeah. So all these, like I said, all these features were compared with the actual DC fault signals from PSCAD, and they match exactly. So that itself shows the robustness of discrete wavelet transform algorithm performing what is. Then after that, basically determine the entropy. Remember, based on the different decomposition levels. So these are all the entropies, and basically based on that, the entropy, the discrete with the wavelet coefficients, that is what is going to be used to basically set the relay to start when the fault occurs. Yeah, so it shows level 1, level 2, level 3, level 4, level 5, level 6, level 7, level